Since the dawn of human consciousness, we have gazed upward at that luminous sphere hanging in our night sky, watching it wax and wane through its eternal dance. The moon has been our timekeeper, our muse, our mystery. It has inspired countless myths, guided ancient navigators across vast oceans, and sparked the imaginations of poets, lovers, and dreamers throughout millennia. Tonight, we embark on a journey through the complete story of Earth's only natural satellite, from its violent birth to its promising future as humanity's next frontier. Long before we understood the moon's true nature, it occupied a central place in human mythology and spirituality. Every culture that has ever gazed upon the heavens has woven stories around that pale disk hanging above. The ancient Sumerians saw the god Nana traversing the night, while the Greeks personified the moon as Selene, driving her chariot across the darkened vault of heaven. The Mayans tracked its movements with a remarkable precision, incorporating lunar cycles into their complex calendar systems that still astound astronomers today. In Chinese mythology, the moon holds the ethereal Chang'e, who fled thereafter consuming an elixir of immortality, forever separated from her earthly love. Japanese tradition speaks of a rabbit living on the lunar surface, pounding mochi rice cakes, a story born from the patterns observers saw in the darker regions, visible even to the naked eye. Hindu tradition associates the moon with Chandra, a deity connected to fertility, plants, and the mind itself. The ancient Egyptians linked the moon to Thoth, god of wisdom and writing, recognizing perhaps the intellectual curiosity that our satellite has always inspired. Indigenous peoples across North America developed intimate relationships with lunar cycles, naming each full moon according to seasonal changes it heralded. The wolf moon of January, the flower moon of May, the harvest moon of September. These names reflected deep observations of nature's rhythms as they synchronized with lunar phases. Native Hawaiian culture developed a lunar calendar so sophisticated that it guided not just agriculture and fishing, but social and spiritual practices as well, with each night of the lunar month carrying its own significance and kapu or sacred restrictions. The moon's influence extended beyond mythology into the practical realm of timekeeping. Before modern calendars, humans organized their lives around lunar phases. The very word month derives from moon, a linguistic fossil preserving this ancient connection. Islamic tradition maintains a purely lunar calendar, with each month beginning at the first sighting of the crescent moon, a practice that ensures religious observances like Ramadan cycle through all seasons over time. Jewish tradition employs a lunar solar calendar, adding extra months periodically to keep festivals aligned with both lunar phases and solar seasons. In medieval Europe, the moon was believed to influence everything from human behavior to agricultural success. Farmers planted crops according to lunar phases, a practice that persists in some communities today, though scientific evidence for its efficacy remains debatable. The very word lunatic reflects the ancient belief that the full moon could affect human sanity, a notion that has proven difficult to completely dispel despite lack of statistical evidence supporting it. Emergency rooms and police stations still occasionally report beliefs in increased activity during full moons, though careful studies repeatedly fail to confirm such patterns. The moon's phases provided humanity with one of its first lessons in predictive science. Ancient observers realized that eclipses followed patterns, that phases repeated with reliable regularity, that this celestial body obeyed rules which could be understood and anticipated. The Greek philosopher Anaxagoras, around 500 BCE, correctly explained that the moon shone by reflected sunlight, and that its phases resulted from viewing different portions of its illuminated half. Such insights represented revolutionary leaps in human understanding, moving from purely mythological explanations toward mechanical ones. Throughout history, the moon served as both inspiration and navigation. Polynesian wayfinders crossed thousands of miles of open ocean using the moon's position along with stars, currents, and wildlife behaviours to guide them between tiny islands. Arab astronomers of the medieval period made detailed observations of lunar motion, developing mathematical models that improved navigation and timekeeping. Their work would eventually flow into European astronomy, contributing to the scientific revolution that would finally begin revealing the moon's true nature. The Romantic poets of the 18th and 19th centuries found in the moon a symbol of beauty, mystery, and melancholy. Byron wrote of the cold white moon looking down upon the earth with mournful eyes. Shelley addressed the moon as pale for weariness of climbing heaven and gazing on the earth. These literary treatments reflected a deep human tendency to project emotion onto that distant sphere, to see in its silver light something that spoke to our inner landscapes. Even as science began explaining the moon's physical reality, it retained its power as metaphor and symbol. In many traditions, the moon carried feminine associations, complementing the masculine sun. This duality appeared across numerous cultures, the yin and yang of Chinese philosophy, the Shiva and Shakti of Hindu thought. The moon's connection to feminine cycles, its monthly waxing and waning echoing biological rhythms, reinforced this symbolism. Whether this association holds any meaningful truth or simply reflects pattern-seeking human minds remains an open question. But the ubiquity of such beliefs across disparate cultures suggests something profound in how humans related to their celestial companion. The moon also featured prominently in early science fiction, serving as the setting for imaginative tales long before such journeys became remotely possible. Lucian of Samosata wrote of travelling to the moon in the 2nd century CE, a fantastical tale involving waterspouts lifting ships into space. In 1638, Bishop Francis Godwin's The Man in the Moon described a journey via harnessed wild swans. Jules Verne's 1865 novel From the Earth to the Moon presented a surprisingly prescient vision of a space cannon launching astronauts moonward from Florida, anticipating by a century the actual launch site of Apollo missions. These stories reflected humanity's ancient dream of reaching that luminous destination hanging tantalizingly in the night. To understand the moon's beginning, we must journey back 4.5 billion years to a solar system barely recognizable compared to the ordered realm we observe today. The sun, recently ignited from its collapsing gas cloud, blazed at the center of a chaotic disk of debris. Planets were still forming through a violent process of accretion, with countless planetesimals objects ranging from mountain-sized to planet-sized careening through space on intersecting orbits. Collisions occurred with staggering frequency, each impact adding mass to growing worlds, or shattering smaller bodies into fragments that would eventually coalesce elsewhere. The young Earth had recently achieved roughly its current mass, having swept up most of the material in its orbital zone. But it was far from alone. Computer simulations suggest that dozens of Mars-sized or larger bodies existed in the inner solar system during this epoch, their gravitational interactions creating an unstable dynamical environment. These protoplanets jostled for position, their orbits gradually shifting through mutual gravitational perturbations. It was only a matter of time before catastrophe struck. The impactor that would create our moon has been named Theia, after the Greek titaness who mothered Selene, the moon goddess. Theia likely formed at one of Earth's Lagrange points regions, where the combined gravity of the Sun and Earth creates stable zones. For perhaps millions of years, Theia grew in size at this gravitational parking spot, eventually reaching roughly the mass of Mars, perhaps 10% of Earth's mass. But Lagrange point stability, while helpful, isn't permanent for large bodies. Eventually, some perturbation perhaps from Jupiter's distant influence, perhaps from the passage of another planetesimal knocked Theia onto a collision course with Earth. The approach happened over thousands of years as orbits gradually intersected. Theia's trajectory brought it toward Earth at a relatively low velocity compared to other potential impacts, perhaps 8 to 10 kilometers per second. This gentle speed proved crucial for the Moon's formation. A head-on collision at higher velocity might have resulted in complete merging or total destruction. Instead, Theia struck Earth at an oblique angle, perhaps 45 degrees from direct impact, delivering what may be the most consequential glancing blow in Earth's history. The collision released energy beyond human comprehension, equivalent to billions of nuclear weapons detonating simultaneously. The impact occurred so swiftly that solid rock behaved almost like fluid, unable to respond mechanically fast enough to the transferred momentum. Theia's core, composed primarily of iron and nickel, plunged deep into Earth's interior. Models suggest most of this dense material merged with Earth's core, explaining why the Moon is notably deficient in iron compared to Earth. But Theia's mantle, the rocky layer surrounding its core, met a different fate. Upon impact, enormous quantities of both Theia's mantle and Earth's outer layers vaporized instantly. Rock heated beyond its boiling point, transforming into a plasma of constituent elements. Other material melted into magma or shattered into fragments, ranging from dust to mountain-sized chunks. This mixture of vapor, liquid, and solid debris exploded outward from the impact site, forming a vast plume that extended thousands of kilometers into space. The event likely lasted only minutes, but those minutes fundamentally reshaped our planet and created the body that would become our Moon. Earth itself survived, though transformed. The impact likely vaporized any atmosphere the young planet possessed and melted its entire surface, creating a global ocean of magma perhaps hundreds of kilometers deep. The planet would have glowed red-hot, radiating energy into space. Any water Earth might have accumulated would have been lost to space, or locked in minerals deep underground. If life had somehow emerged on Earth before this cataclysm, an unlikely prospect, the giant impact would have sterilized the planet completely. The debris ejected by the impact entered orbit around Earth, forming a disk of material extending from just above Earth's surface to perhaps 3 times the current Moon's distance. This proto-lunar disk contained an estimated 2 to 3 lunar masses of material, far more than would eventually coalesce into our Moon. Much of this material fell back to Earth over subsequent days and weeks, adding to the molten chaos below. But enough remained in orbit to begin the formation process. Within this disk, physics took over. Particles collided, sometimes sticking together, sometimes fragmenting further. The disk likely began spreading, with inner material migrating inward to fall back to Earth, while outer material expanded further from the planet. This process, driven by the transfer of angular momentum and by tidal forces, concentrated material in regions where stable orbits existed. The hottest material, the vaporized rock, began to cool and condense into tiny droplets of molten material. These droplets collided with solid fragments, forming larger aggregates. Computer simulations suggest the Moon coalesced remarkably quickly by geological standards. Within a matter of months or years, gravitational attraction drew material together into ever larger clumps. The largest of these moonlets grew fastest, their stronger gravity allowing them to accrete material more efficiently. Soon one dominant body emerged, sweeping up the surrounding debris and establishing itself as the primary satellite. Smaller moonlets either merged with this primary body or were ejected from the system or sent crashing into Earth. The newborn moon formed much closer to Earth than its current position. Estimates suggest perhaps 15,000 to 20,000 kilometers distant, compared to today's average of 384 to 400 kilometers. At such proximity, Earth would have dominated the lunar sky, appearing roughly 15 times larger than the moon appears from Earth today. Tidal forces between the two bodies would have been tremendously powerful, roughly 1,000 times stronger than current tides. These forces played a crucial role in the moon's early evolution and continue to shape the Earth-Moon system today. Evidence supporting this giant impact hypothesis comes from multiple sources. The moon's composition closely matches Earth's mantle, but differs significantly from Earth as a whole. Exactly what we would expect if the moon formed primarily from Earth's outer layers and Theia's mantle while the dense cores merged with Earth. The moon is notably depleted in volatile elements, substances that vaporize easily consistent with formation from a superheated impact-generated disk where volatiles would have escaped to space. The moon's relative lack of iron, its low density compared to Earth, and the similarities in oxygen isotope ratios between Earth and moon rocks all point toward this common origin. The Apollo program provided the crucial samples needed to test formation theories. When scientists analysed rocks brought back from the lunar surface, they found ages clustering around 4.5 billion years, matching the age of the solar system itself and supporting formation during the solar system's chaotic early period. The rock's composition, their depletion in volatiles, and their isotopic signatures all aligned with predictions of the giant impact model. Alternative theories, such as the moon forming elsewhere and being captured by Earth's gravity, or forming alongside Earth from the same disk of material, struggled to explain these observations. Yet mysteries remain. Recent high-precision measurements reveal that Earth and Moon match each other's isotopic composition far more closely than models typically predict. If they are formed at a different location in the solar system, its isotopic signature should differ somewhat from Earth's. The near-perfect match suggests either that Theia formed very close to Earth, possibly at a Lagrange point, or that the impact and subsequent disk evolution mixed material so thoroughly that any differences disappeared. Scientists continue refining models to explain this puzzling similarity. Some researchers have proposed alternative scenarios. Perhaps Theia was much larger than Mars-sized, and the impact generated so much mixing that distinct compositions homogenized. Perhaps multiple impacts occurred, with Theia's collision being merely the largest. Perhaps the impact occurred earlier than currently thought, allowing more time for isotopic signatures to equilibrate. These variations on the giant impact theme demonstrate that while we understand the broad picture, details remain subjects of active research and occasionally heated scientific debate. Regardless of these details, the giant impact hypothesis successfully explains the moon's fundamental characteristics: its size relative to Earth, unusually large for a planetary satellite; its composition, similar to Earth's mantle but depleted in iron and volatiles; its orbital characteristics, roughly aligned with Earth's equator; and its age, coeval with Earth. No alternative theory explains these features as comprehensively. The violence that created our moon gave Earth its largest satellite and set in motion processes that would profoundly influence our planet's evolution and eventually the emergence of life. Imagine the moon in its infancy, a world utterly alien to the cold, grey sphere we know today. The newly formed satellite glowed red from the heat of formation, its entire surface molten or semi-molten. This global ocean of magma, called the lunar magma ocean, likely extended from the surface down hundreds of kilometers, perhaps encompassing the entire moon. Temperatures exceeded 200 degrees Celsius, hot enough to melt rock completely. This infernal landscape represented the starting point from which the moon's current features evolved. The magma ocean didn't remain molten indefinitely. Heat radiated into the vacuum of space with ruthless efficiency, lacking any atmosphere to provide insulation. The surface began cooling first, developing a thin crust of solidified material. But this early crust proved unstable. Convection currents in the magma below broke through, allowing hot material to rise and cold material to sink in a continuous cycle. The surface likely resembled a slow-motion sea of lava, with rafts of solid crust floating on molten rock, occasionally breaking apart and being consumed by the liquid beneath. As cooling progressed, minerals crystallized from the magma in a specific sequence determined by their melting points. Olivine and pyroxene iron and magnesium-rich silicate minerals crystallized first. Being denser than the surrounding liquid, these crystals sank toward the moon's interior, accumulating in layers at depth. This process concentrated these elements in the lunar mantle while depleting the remaining liquid in iron and magnesium. The differentiation process, where heavier materials sink and lighter ones rise, shaped the moon's internal structure. Meanwhile, lighter minerals remained in the liquid or crystallized later. Plagioclase, feldspar, a calcium and aluminum-rich mineral crystallized, but being less dense than the magma, these crystals floated upward. Over millions of years, floating plagioclase accumulated at the surface, forming a distinct layer that would become the lunar crust. This flotation process explains why the lunar highlands, the bright, heavily cratered regions covering most of the moon's surface, consist primarily of anorthosite, a rock composed almost entirely of plagioclase feldspar. The crystallization process left behind a residual liquid enriched in elements incompatible with the common minerals that had already solidified. This remaining melt contained higher concentrations of potassium, rare earth elements, and phosphorus, collectively termed creep by lunar scientists. This creep-rich material eventually crystallized between the crust and mantle, forming a layer that would later fuel volcanism and influence the moon's thermal evolution. Rocks enriched in creep have distinctive chemical signatures that helped scientists understand lunar differentiation processes. Perhaps 100 million years after formation, the magma ocean had largely solidified. The moon possessed a distinct layered structure. A small iron core, perhaps 300 to 400 kilometers in radius. A thick mantle of olivine and pyroxene extending upward thousands of kilometers. And a crust of anorthosite perhaps 40 to 50 kilometers thick. Thicker on the far side than the near side facing Earth. This asymmetry in crustal thickness would prove important for understanding why the near and far sides look so different today. But the young moon's trials had barely begun. The solar system remained a shooting gallery of debris. Rocky planetesimals that hadn't yet accreted onto planets continued orbiting the sun in vast numbers. Many crossed the moon's orbital path, inevitably leading to impacts. The period from roughly 4.1 to 3.8 billion years ago saw an increase in impact rates, an event termed the Late Heavy Bombardment. Whether this represented a true spike in impacts, or simply the tail end of a gradually declining bombardment rate, remains debated, but the effects on the moon were profound. Large impacts blasted enormous craters into the lunar surface. The biggest of these impacts created basins hundreds of kilometers across. The South Pole Aitken Basin, the largest impact structure on the moon, and one of the largest in the solar system, stretches 2,500 kilometers in diameter and reaches depths of 8 kilometers below the surrounding terrain. This colossal impact excavated material from deep in the crust possibly even exposing mantle rocks. Other major impacts created the Imbrium, Serenitatis, Chrysium, and numerous other basins that dominate the lunar near side. These basin-forming impacts released tremendous energy, fracturing and heating rock over vast areas. The impacts likely melted enormous volumes of material, creating sheets of impact melt that flooded basin floors and spilled over rims. As this melt cooled, it formed distinctive rocks that helped scientists later determine the age of major basins through radiometric dating. The impacts also excavated and redistributed enormous quantities of crustal material, creating blankets of ejecta that buried and modified earlier terrain across the lunar surface. Between major impacts, countless smaller ones peppered the surface. Every square metre of the moon's surface has been struck multiple times by meteoroids ranging from dust grains to boulder-sized objects. This continuous bombardment fragmented and mixed surface materials, creating a layer of broken rock called regolith. On the oldest terrains, this regolith extends metres deep, a testimony to billions of years of impacts. The regolith's loose, fragmented nature would later challenge Apollo astronauts, who sometimes sank ankle-deep in the powdery material. The impacts of the late heavy bombardment also had thermal consequences. Large impacts delivered enormous amounts of energy, heating local regions and possibly partially remelting portions of the mantle. This heating, combined with heat still remaining from the moon's formation and heat generated by radioactive decay of elements like uranium, thorium, and potassium, created conditions favourable for volcanism. Starting perhaps 3.8 billion years ago, lunar volcanism began flooding major impact basins with lava. These volcanic eruptions differed significantly from volcanic activity on Earth. Lunar lavas were extremely fluid, with viscosities similar to motor oil, allowing them to flow vast distances across basin floors. The lavas consisted primarily of basalt, a dark rock rich in iron and magnesium. Multiple eruptions over hundreds of millions of years built up layers of basalt, hundreds of meters thick in some locations, filling impact basins and creating the dark features we call Maria Latin for seas, though they contain no water and never did. The Maria formed primarily on the near side of the moon, with the far side remaining largely dominated by lighter-coloured highlands. This asymmetry puzzled scientists until they realised the crust's thickness plays a crucial role. The thinner crust on the near side allowed magma to more easily reach the surface through fractures created by impacts. The far side's thicker crust acted as a barrier, preventing most magma from erupting. Additionally, the concentration of creep beneath the near side crust provided more heat-producing radioactive elements, potentially making it easier for magma to ascend in those regions. Volcanic activity peaked between roughly 3.8 and 3.2 billion years ago, then gradually declined. The last widespread mare volcanism occurred around 1.2 billion years ago, though some evidence suggests isolated small eruptions might have continued until as recently as 100 million years ago. As the moon's interior cooled, magma generation decreased and eventually ceased entirely. Today, the moon is volcanically dead, its interior having cooled to the point where melting no longer occurs. During this era of volcanism and bombardment, the moon's relationship with Earth continued evolving. Tidal forces, the differential gravitational pull that Earth's gravity exerts across the moon's diameter, gradually slowed the moon's rotation. Initially, the moon likely rotated much faster, perhaps completing a full rotation every few hours. But Earth's gravity pulled more strongly on the moon's near side than on its far side, creating a torque that dissipated the moon's rotational energy. Over perhaps hundreds of millions of years, this tidal braking slowed the moon's rotation until it became tidally locked rotating once per orbit. always keeping the same face toward Earth. This tidal locking explains why we only ever see one side of the Moon from Earth. The far side remained hidden until Soviet spacecraft photographed it in 1959, revealing a surface markedly different from the familiar near side. The process that locked the Moon's rotation also affected the Moon's interior. The tidal forces likely generated heat through friction, possibly extending the period of volcanic activity. Tidal heating continues today, though at much reduced levels, generating tiny amounts of heat in the Moon's interior. The young Moon also influenced Earth profoundly. Recall that it orbited much closer than today, meaning tidal forces on Earth were far stronger. The Moon raised enormous tides in Earth's oceans once they formed after the giant impact's heat dissipated. These tides may have been hundreds of meters high, vastly greater than modern tides. The tidal friction, as Earth rotated beneath these tidal bulges, slowed Earth's rotation, lengthening the day. 4 billion years ago, an Earth day likely lasted only about 6 hours. The Moon's tidal influence gradually lengthened this to our current 24-hour period. The same tidal friction that slowed Earth's rotation had an opposite effect on the Moon. The energy dissipated from Earth's rotation didn't vanish. Conservation of angular momentum demanded it go somewhere. It went into the Moon's orbit, gradually pushing the Moon further from Earth. This outward migration continues today, at roughly 3.8 centimeters per year, measured precisely by bouncing laser beams off reflectors left by Apollo astronauts. Over billions of years, this gradual recession has moved the Moon from perhaps 20,000 kilometers distant to its current 384,400 kilometers. By about 3 billion years ago, the Moon had achieved roughly its modern form. The major impact basins had been excavated and filled with lava. The heavy bombardment had declined to more modest levels. Volcanic activity was waning. The surface had cooled, with daytime temperatures on the equator still reaching scorching levels above 120 degrees Celsius, but nighttime temperatures plunging to minus 170 degrees Celsius in the absence of an atmosphere to retain heat. The Moon had transitioned from a dynamic, evolving world to a more static body, where changes occurred slowly, if at all. Our Moon is no mere ornament in the sky, no passive companion orbiting our planet without consequence. Instead, it represents an active force that has shaped Earth's evolution in fundamental ways, influencing everything from the length of our day to the stability of our climate, from the power of ocean tides to possibly the emergence of life itself. Understanding these influences reveals that Earth without the Moon would be a profoundly different world, perhaps even one inhospitable to complex life. The most obvious and immediate effect of the Moon involves tides. Ancient observers recognized that ocean tides correlated with the Moon's position, rising and falling roughly twice per day, in sync with the Moon's transit across the sky. What causes this phenomenon? Gravity. But it's not simply that the Moon pulls on Earth after all. Earth pulls on the Moon equally hard by Newton's third law. Rather, tides result from the Moon's gravitational force varying across Earth's diameter. The side of Earth facing the Moon experiences stronger gravitational pull than Earth's centre, which in turn experiences stronger pull than the side facing away. This differential force, the tidal force, stretches Earth along the Earth-Moon axis. For rigid Earth rock, this stretching amounts to perhaps 30 centimetres, barely noticeable. But Earth's oceans respond much more dramatically, being fluid and mobile. Water on the side facing the Moon gets pulled slightly toward the Moon, creating a bulge. Surprisingly, water on the opposite side also bulges outward, not because the Moon pulls it, but because Earth's centre gets pulled away from that water, leaving it behind. These two tidal bulges, one facing the Moon, one opposite, explain why most locations experience 2 high tides daily. As Earth rotates, Any given location passes through both bulges during a 24-hour period. The sun also creates tides through the same mechanism, though solar tides are only about 46% the strength of lunar tides, despite the sun's greater mass. Because tidal force depends on both mass and distance, falling off with the cube of distance. When the sun and moon align during new and full moons, their tides add together, creating especially high spring tides. When they're perpendicular during quarter moons, they partially cancel, producing smaller neap tides. The reality of tides proves more complex than this simple picture suggests. Earth's continents interrupt the flow of tidal bulges, creating resonances and reflections that produce wildly different tidal ranges at different locations. The Bay of Fundy in Canada experiences tides exceeding 16 metres, the highest in the world, due to the bay's funnel shape resonating with tidal periods. Other locations experience single daily high tides rather than two. Some areas see minimal tidal range. Predicting tides requires accounting for these local effects, a task that kept mathematicians and astronomers busy for centuries. But tides do more than raise and lower sea levels. The tidal bulges attempt to align with the moon, pointing directly toward and away from it. However, friction within Earth in the oceans, in the solid Earth itself, prevents perfect alignment. Earth's rotation drags the tidal bulges slightly ahead of the moon. This misalignment has profound consequences. The offset bulge exerts gravitational pull on the moon. The bulge ahead of the moon pulls it forward in its orbit, transferring energy from Earth's rotation to the moon's orbital motion. This transfer slows Earth's rotation, lengthening the day, while pushing the moon to higher orbits, increasing the month's length. This tidal interaction has operated throughout Earth-Moon history. 4 billion years ago, with the moon much closer, tidal forces were far stronger and days much shorter. Coral fossils from 400 million years ago show growth patterns suggesting roughly 400 days per year, meaning days lasted about 22 hours then. Extrapolating backward, the moon formed when Earth's day may have been only 4 to 6 hours long. The gradual lengthening of the day has provided life on Earth with slowly changing environmental rhythms, though whether this mattered for evolution remains speculative. The tidal interaction also stabilizes Earth's rotation axis. Earth spins like a top, with its axis tilted 23.5 degrees relative to its orbital plane around the Sun. This tilt creates our seasons. When the northern hemisphere tilts toward the Sun, it experiences summer, while the southern hemisphere has winter. But a spinning top wobbles, and Earth is no exception. Various forces cause Earth's rotational axis to trace out a slow circle completing one cycle every 26,000 years. Additionally, the tilt angle itself changes over cycles of about 41,000 years, varying between roughly 22 and 25 degrees. These variations would be far more extreme without the moon. Computer simulations of Earth-like planets without large moons show their rotation axes can vary chaotically, sometimes experiencing dramatic tilts that could swing from near 0 degrees to 90 degrees or more over millions of years. Such variations would create catastrophic climate swings. Imagine Earth with its poles pointed toward the Sun for extended periods, creating seasons of unimaginable extremes. The moon's gravitational influence on Earth's equatorial bulge Earth is slightly wider at the equator than pole to pole due to rotation exerts a stabilizing torque that keeps the axial tilt within a narrow range. This stabilization may have been crucial for life's evolution. While life is remarkably adaptable, extreme climate variations might prevent the establishment of stable ecosystems that allow complex life to emerge. The moon's stabilizing influence has maintained relatively consistent seasonal patterns for billions of years, allowing life to adapt to predictable climate cycles. Mars, with only tiny moons providing negligible, stabilizing torque, has experienced wild obliquity variations that may have contributed to its current frozen, desiccated state. The Moon may also have influenced Earth's magnetic field. Earth's core consists of a solid inner core surrounded by a liquid outer core of iron and nickel. Convection. In this liquid outer core, driven by heat escaping from the core and by compositional differences, as the solid inner core grows, generates Earth's magnetic field through a dynamo effect. This magnetic field shields Earth's surface from solar wind-charged particles streaming from the Sun and cosmic rays, preventing them from stripping away Earth's atmosphere and damaging DNA in living organisms. Some scientists have proposed that tidal heating from the Moon, though small today, might have been significant in Earth's early history when the Moon orbited much closer. This additional heat source could have enhanced core convection, helping establish a strong magnetic field earlier than might otherwise have occurred. The evidence remains circumstantial, but the possibility illustrates how the Moon's influence might extend even to Earth's interior dynamics. A strong early magnetic field would have been particularly important when the young Sun was more active and energetic, producing a stronger solar wind capable of eroding planetary atmospheres. The tides themselves may have aided life's emergence. Life likely originated in the oceans, but many theories propose that tidal pools regions repeatedly wet and dried by tidal action provided ideal conditions for concentrating and organizing the complex chemistry needed for life. The cycle of wetting and drying could have driven the assembly of primitive cell membranes and promoted the polymerization of molecules like RNA. While life's origin remains one of science's greatest mysteries, tidal environments created by the Moon certainly provided unique chemical laboratories that might have facilitated the transition from chemistry to biology. Tides also influence marine life today. Many organisms have evolved to exploit tidal cycles. Intertidal species time their reproductive cycles to tides, releasing eggs or sperm when water levels are optimal. Grunion fish famously spawn on California beaches during spring tides, laying eggs in sand that remains dry until the next spring tide 2 weeks later. Horseshoe crabs, living fossils that have remained essentially unchanged for hundreds of millions of years, emerge from the sea to lay eggs on beaches during full and new moons. Coral spawning events, where vast numbers of corals simultaneously release eggs and sperm, often occur during specific lunar phases. These biological connections to the Moon extend even to terrestrial life. Some studies suggest bird migration patterns, animal breeding cycles, and plant growth may show correlations with lunar phases, though the evidence remains mixed and controversial. What's clear is that for many organisms, particularly those living in coastal environments, the Moon's influence remains palpable and important. The Moon has shaped not just Earth's physical characteristics, but the adaptations and behaviours of life that has evolved here. The Moon also plays a role in Earth's climate system, though more subtle than often claimed. Some researchers have investigated whether lunar tidal forces could trigger earthquakes or volcanic eruptions. While the Moon does create measurable stresses in Earth's crust, solid Earth tides, these stresses are tiny compared to those that cause earthquakes. Statistical studies have found weak correlations between lunar phases and earthquake occurrence, but the effect is small and may not be causally significant. Similarly, while tidal forces might occasionally trigger eruptions in volcanoes already primed to erupt, they don't appear to be a major factor in volcanism. More significantly, tidal mixing in the oceans influences global climate. Tides create currents, particularly in shallow seas and around obstacles like seamounts. These currents generate turbulence that mixes surface and deep waters. This mixing plays a role in the global ocean circulation system, including the thermohaline circulation, the conveyor belt of currents driven by temperature and salinity differences that distributes heat around the planet. Some models suggest tidal mixing contributes significantly to maintaining this circulation. Without tides or with weaker tides, ocean mixing patterns would change, potentially affecting climate. The Moon also affects Earth through less direct pathways. Its presence stabilizes the Earth-Moon barycenter, the center of mass around which both bodies orbit, located inside Earth about 4,700 kilometers from Earth's center. This barycenter traces out Earth's orbit around the Sun, while Earth itself wobbles around it. This wobble slightly affects Earth's distance from the Sun over the course of each month, creating tiny variations in the solar heating Earth receives, though these variations are too small to significantly impact climate. Looking at the broader picture, the Earth-Moon system remains somewhat unusual among planets. Few terrestrial planets have moons at all. Mercury and Venus have none, while Mars hosts 2 tiny captured asteroids. Giant planets typically have extensive moon systems, but these moons are small relative to their planets. Earth's moon is unusually large relative to Earth, containing about 1.2% of the Earth-Moon system's total mass. This ratio exceeds all other planet-moon pairs, except Pluto-Charon, which some astronomers consider a double dwarf planet rather than a planet-moon system. This unusual configuration has led some scientists to describe Earth and the Moon as a double planet system. While the Moon clearly orbits Earth rather than both bodies orbiting a point in space between them, the dynamics of the system differ noticeably from those of a planet with a small negligible mass satellite. The Moon's substantial mass affects Earth measurably, creating the tides and orbital dynamics we've discussed. Whether Earth's habitability required such a large moon remains an open question, one that we may begin answering as we discover and characterize more exoplanets and potentially detect exomoons around them. Let us embark on a comprehensive tour of the Moon's surface, exploring the major features that define its geography and the geological processes that created them. From Earth, even binoculars reveal dramatic differences in lunar terrain, bright regions, dark patches, and if you look carefully during favourable angles and lighting, a few prominent craters with bright ray systems extending across the surface. With a telescope, the view becomes increasingly intricate, revealing countless craters, mountain ranges, valleys, and other features that have captivated lunar observers for centuries. The most obvious features are the Maria and Highlands. The Maria, those dark patches visible to the naked eye, cover about 16% of the lunar near side, but only 2% of the far side. These seas received their name from early astronomers who believed they might actually contain water. Instead, they consist of basaltic lava flows that erupted billions of years ago, filling major impact basins. The largest Maria include Mare Imbrium, Sea of Rains, Mare Serenitatis, Sea of Serenity, Mare Tranquillitatis, Sea of Tranquility, Oceanus Procellarum, Ocean of Storms, and others named for various weather phenomena, emotional states, and other evocative concepts. Each mare represents millions of years of volcanic activity. Mare Imbrium, for instance, fills the basin created by a massive impact roughly 3.9 billion years ago. Subsequent eruptions over the next several hundred million years flooded the basin with layer upon layer of basalt. The youngest mare, Mare Orientale, formed around 3.8 billion years ago, while some small mare patches show evidence of volcanism as recent as 1.2 billion years ago, based on crater counting techniques and isotopic dating of return samples. The basalts forming the Maria differ in composition and age across different Maria, creating subtle colour variations detectable in detailed photographs. Some Maria show reddish tints indicating higher titanium content, while others appear bluer. These compositional differences reflect variations in the source regions deep in the lunar mantle where the magmas originated. Mare Tranquillitatis basalts are particularly rich in titanium, while Mare Crisium basalts contain lower amounts. These variations help scientists understand the moon's interior structure and the evolution of lunar volcanism. Within the Maria, careful observers can spot wrinkle ridges, long sinuous ridges that snake across Mare surfaces. These features formed as the Mare basalts cooled and contracted, causing the surface to buckle and fold. Some ridges represent places where later lava flows overran earlier ones. Others mark thrust faults, where sections of the Mare floor compressed and pushed upward. The presence of these compressional features indicates the Maria shrank slightly as they cooled, a testament to the thermal stresses acting on these ancient lava plains. Contrasting with the dark Maria, the lunar highlands appear bright and heavily cratered. These regions consist primarily of anorthosite rock composed almost entirely of plagioclasa feldspar. The highlands represent the moon's original crust, dating back to the solidification of the lunar magma ocean 4.4 billion years ago. Because they're older than the Maria, they've accumulated far more impact craters, giving them their characteristic heavily pockmarked appearance. Some highland regions are so densely cratered that new impacts can only form by destroying or overlapping older craters, a state called saturation cratering. Craters dominate the lunar landscape, ranging from microscopic pits in individual rocks to basins spanning thousands of kilometres. Each crater tells a story of cosmic violence, of meteoroids and asteroids striking the moon at velocities measured in kilometres per second. The kinetic energy of these impacts, 1/2 mass times velocity, squared transforms into heat and motion, excavating craters many times larger than the impactor itself. Small, simple craters exhibit bowl shapes with raised rims and depths roughly 1/5 their diameter. These craters form when relatively small impactors, up to perhaps 15 kilometres in diameter, strike the surface. The impact vaporizes the impactor and some target rock, while shock waves radiate outward, fracturing and ejecting material. The crater grows by excavation, as shocked rock flows outward and upward, piling up around the rim. This excavated material, the ejector blankets the surrounding terrain, burying pre-existing features and creating rays of bright material extending radially from young craters. Tycho, one of the moon's most prominent craters, displays spectacular rays extending halfway across the lunar near side. These rays consist of bright ejecta from the impact that formed Tycho roughly 108 million years ago. The rays remain bright because they haven't yet been darkened by the gradual weathering processes that affect the lunar surface. Given enough time, hundreds of millions to billions of years, the rays will darken and blend with surrounding terrain, explaining why ancient craters lack visible rays, even though they surely formed them initially. Larger impacts create complex craters with central peaks, terraced walls, and flat floors. When craters exceed roughly 15 to 20 kilometers in diameter, the excavation process becomes more complicated. The transient crater, the initial bowl-shaped cavity, collapses under gravity. The crater walls slump inward, forming terraces. The floor rebounds upward, creating a central peak consisting of material uplifted from depth. The largest complex craters can reach several hundred kilometers in diameter, with multiple rings of peaks and highly modified structures. The very largest impacts create multi-ring basins. Orientale, on the moon's western limb, as viewed from Earth, beautifully displays this structure. A central basin floor sits surrounded by 3 concentric mountain rings. the outermost extending 930 kilometers in diameter. Other major basins include Imbrium, Serenitatis, Chrysium, Nectaris, and the colossal South Pole Aitken Basin mentioned earlier. These basins formed during the Moon's first 700 million years, when impact rates were far higher than today. Later, volcanic eruptions partially or completely filled many basins with mere basalts. The mechanics of basin formation remain incompletely understood. The concentric rings likely represent uplift features similar to central peaks but on a vastly larger scale. The enormous energy of basin-forming impacts, equivalent to millions of nuclear weapons, creates shockwaves powerful enough to melt rock and trigger complicated rebound dynamics. Models suggest these impacts fractured the crust to great depths, possibly allowing magma to well up from the mantle, explaining why many basins later filled with lava. Between craters, the lunar surface shows other distinctive features. Rills channel-like structures appear in several varieties. Sinuous rills meander across mare surfaces, sometimes for hundreds of kilometers. These channels almost certainly formed as lava tubes or channels, conduits through which molten basalt flowed across the surface. Some sinuous rills begin at small volcanic vents and wind downslope, gradually fading as the lava flow spread and thinned. Hadley Ryle, visited by Apollo 15 astronauts, measures up to 400 meters deep and 1.5 kilometers wide in places, giving astronauts spectacular views into the Moon's volcanic past. Straight rills represent fractures or faults in the lunar crust. These features formed as portions of the crust shifted relative to one another, creating linear chasms. Some straight rills formed as the crust adjusted to the weight of mare basalts, loading impact basin floors. Others developed as the Moon cooled and contracted slightly, creating stresses that fractured the brittle crust. Arcuate rills curve around mare margins, likely representing slumping of mare material or adjustment of the underlying basin structure. The lunar highlands also feature mountain ranges, though these differ fundamentally from terrestrial mountains. Earth's mountains typically form through plate tectonics, the collision of tectonic plates pushing rock upward, or through volcanic activity building cones and shields. The Moon lacks plate tectonics, being too small and cool to maintain the mantle convection that drives plate motions on Earth. Instead, lunar mountains represent uplift from major impacts. The Montes Apenninus, rising along the southeastern rim of Mare Imbrium, reach heights exceeding 5,000 meters above the Mare floor. These mountains formed as the enormous impact that created the Imbrium basin thrust rock upward, creating a ring of peaks around the basin rim. Similarly, the Montes Caucasus, Montes Alpes, and other mountain ranges trace the rims of ancient impact structures. Some isolated peaks within basins represent central peaks of complex craters, later surrounded by lava that flooded the crater floor. Examining the Moon's far side reveals striking differences from the familiar near side. The far side consists almost entirely of heavily cratered highlands with only small patches of mare basalts. The South Pole Aitken Basin dominates the southern far side, its interior showing slightly darker material, but nothing like the extensive mare flooding seen on the near side. This hemispheric dichotomy reflects the Moon's internal structure. The thicker crust on the far side inhibited volcanic eruptions, while the near side's thinner crust and greater concentration of heat-producing elements allowed more extensive volcanism. No one realized the far side looked so different until 1959, when the Soviet Lunar 3 probe returned the first images of the hidden hemisphere. Before then, astronomers could only speculate about what lay on the perpetually averted face. Some theorized it might look identical to the near side, just a continuation of the same terrain. The actual images surprised everyone, revealing the stark differences that lunar scientists still work to fully explain. Understanding this asymmetry provides insights into the moon's thermal evolution and the processes that shaped its surface. The lunar poles present particularly intriguing terrain. Both polar regions contain areas that never receive direct sunlight, permanently shadowed regions inside deep craters where sunlight never reaches the floors. These perpetual shadows have existed for billions of years, maintaining temperatures below 40 Kelvin, minus 233 degrees Celsius. At such cold temperatures, water ice and other volatile substances can remain stable for geological time periods, potentially creating deposits of frozen water in these regions. Recent missions have confirmed water ice exists in permanently shadowed craters at both poles. The Lunar Reconnaissance Orbiter, using radar and neutron detectors, has mapped hydrogen concentrations consistent with water ice. India's Chandrayaan-1 mission detected spectral signatures of water ice on the surface. The water likely came from comet impacts and from chemical reactions between solar wind protons and oxygen in lunar rocks, processes that have operated throughout lunar history. This ice represents a potential resource for future human explorers, providing water, oxygen, and rocket fuel without needing to transport these materials from Earth. The lunar surface exhibits more than just craters and volcanic plains. At smaller scales, the moon is covered in regolith, a layer of fragmented rock created by billions of years of meteoroid impacts. Every exposed surface has been struck repeatedly by impactors ranging from micrometeorites to boulder-sized rocks. These impacts shatter bedrock, creating a loose layer of debris that mantles the entire moon. The regolith typically extends several meters deep on ancient terrains, becoming thinner on younger surfaces where less time has passed for impacts to accumulate. Within the regolith, careful searchers can find unusual specimens. Glass beads formed when impact-melted droplets cooled in flight litter the surface. Agglutinates, tiny fragments of rock welded together by microscopic glass, constitute a major component. Some rocks show breccia textures, fragments of various rocks cemented together by impact processes, evidence of the violent history these materials have experienced. Meteorite fragments from the impactors themselves occasionally turn up, providing samples of asteroids delivered conveniently to the lunar surface. The regolith gradually darkens over time through a process called space weathering. Solar wind ions, mostly protons and electrons, constantly bombard the lunar surface. Being electrically charged, they get channeled by the moon's weak magnetic fields and local electric fields. This bombardment breaks chemical bonds in minerals, creating nanoscale metallic iron particles that darken the regolith and alter its spectral properties. Micrometeorite impacts add to this process, vaporizing tiny amounts of material that recondense as dark coatings. Fresh craters appear bright because they expose material from depth that hasn't experienced space weathering, but given millions of years, even these fade to match their surroundings. Exploring the moon's composition requires examining both returned samples and remote sensing data. The 382 kilograms of rock and soil returned by Apollo astronauts, plus additional samples from Soviet lunar missions, provide ground truth for understanding lunar geology. These samples revealed the moon's antiquity. Most rocks date between 3.1 and 4.4 billion years old. They confirmed the moon's bone-dry nature, with water concentrations millions of times lower than Earth rocks. They showed the moon's depletion in volatile elements and enrichment in refractory elements that don't vaporize easily. Remote sensing from orbit has extended our understanding globally. Instruments measuring reflected light at various wavelengths can identify minerals based on their spectral signatures. Gamma-ray and neutron spectrometers can detect elements based on the radiation they emit when struck by cosmic rays. Laser altimeters map the moon's topography with meter-level precision, revealing subtle features invisible from Earth. Synthetic aperture radar can detect deposits in permanently shadowed craters and measure roughness at centimetre scales. These techniques have revealed deposits of olivine and pyroxene near the South Pole Aitken Basin, consistent with excavation of mantle material by that enormous impact. They have identified unusual silica-rich domes that might represent a type of volcanism different from the more common basaltic eruptions. They found deposits of plagioclase-rich material that could represent ancient crustal samples useful for understanding early lunar history. Each new mission adds to our knowledge, painting an increasingly detailed picture of lunar geology. Humans have observed the moon for as long as our species has existed, but transforming observations into understanding required millennia of careful watching, recording, and theorizing. The journey from seeing the moon as a divine entity or celestial ornament to recognizing it as a world with its own geography represents one of humanity's great intellectual achievements, involving contributions from cultures across the globe and spanning thousands of years. The earliest systematic lunar observations came from Babylonian astronomers in ancient Mesopotamia, beginning around 1800 BCE. These careful watchers recorded lunar positions, phases and eclipses on clay tablets, accumulating centuries of data. They recognized that lunar eclipses occurred only at full moon, when the moon passed through Earth's shadow, and that eclipses followed predictable cycles. The Saros cycle, a period of roughly 18 years and 11 days, after which eclipse patterns repeat, was known to Babylonian astronomers and later transmitted to Greek scholars. The Greeks inherited and expanded upon this knowledge. Thales of Miletus, around 600 BCE, correctly predicted a solar eclipse, demonstrating understanding of eclipse mechanisms. Anaxagoras proposed that the moon shone by reflecting sunlight, explaining both its phases and the darkening during lunar eclipses. Aristotle provided evidence for Earth's sphericity by noting that Earth's shadow on the moon during eclipses always appeared circular, possible only if Earth were spherical. Aristarchus of Samos, around 270 BCE, attempted to measure the relative distances of the Sun and Moon through geometrical reasoning. Though his measurements proved inaccurate due to observational limitations, his method was sound. He observed that during a half-moon, the angle between the Sun and Moon, as viewed from Earth, should be just short of 90 degrees. By measuring this angle precisely, he could calculate the ratio of Sun to Earth distance versus Moon to Earth distance. His measurements suggested the Sun was about 20 times farther than the Moon. The actual ratio is about 390. But the attempt represented sophisticated astronomical thinking. Hipparchus of Nicaea, perhaps the greatest observational astronomer of antiquity, lived around 150 BCE. He measured the moon's distance using parallax, the apparent shift in the moon's position when viewed from different locations on Earth. During a solar eclipse visible as total from one location, but partial from another, he could use geometrical relationships to calculate the moon's distance. His results suggested the moon lay about 59 times Earth's radius away, remarkably close to the average value of 60 Earth radii we know today. Ptolemy, working in Alexandria around 150 CE, compiled astronomical knowledge into his masterwork, the Almagest. This treatise included detailed tables for predicting lunar positions, accounting for the moon's complex motions, including its varying orbital speed and slight wobbles. Ptolemy's geocentric model, which placed Earth at the centre with the moon, sun, planets, and stars revolving around it in complicated circular motions, dominated astronomical thinking for 1,400 years, despite its inaccuracies. During Europe's medieval period, Islamic scholars preserved and extended Greek astronomical knowledge. Al-Battani, working in Syria around 900 CE, made precise measurements of the moon's motion and improved calculations of lunar and solar eclipses. Ibn Yunus in Egypt around 1000 CE compiled extensive tables of lunar observations. Alhazen wrote on the moon's optical properties, attempting to explain why the moon appears larger near the horizon than overhead, a puzzle that still generates debate, as the effect is purely psychological despite numerous proposed explanations involving atmospheric refraction. The invention of the telescope in the early 1600s revolutionized lunar observation. Galileo Galilei, turning his improved telescope skyward in 1609, saw features no human had seen before. Mountains and valleys became visible, their shadows shifting with changing solar illumination. Dark spots and bright regions showed clear boundaries. The moon's surface, Galileo realized, resembled Earth's a rough, varied world, not the perfect crystalline sphere of Aristotelian philosophy. His sketches and descriptions, published in Sidereus Nuncius, Starry Messenger, in 1610, helped overturn ancient cosmologies and establish that celestial bodies were physical objects subject to examination and understanding. Other early telescopic observers added details. Johannes Hevelius published Selenographia in 1647, containing detailed maps of lunar features and introducing nomenclature that persists today. Giovanni Riccioli, in 1651, named many craters after famous astronomers and philosophers, Copernicus, Tycho, Ptolemy, Kepler, and others, creating a lunar pantheon of scientific heroes. This naming system, though modified and extended, remains in use, with prominent craters bearing names of notable scientists. The invention of the reflecting telescope by Newton and others allowed larger apertures and better resolution. Observers compiled increasingly detailed maps, noting subtle features and attempting to understand their origins. Theories proliferated about lunar craters. Were they volcanic calderas like those on Earth? This seemed reasonable given that many craters contained central peaks and reminded observers of terrestrial volcanoes. Perhaps the moon had once been volcanically active, leaving these scars on its surface. The volcanic theory for lunar craters persisted into the 20th century, despite challenges. Some observers noted that the circular shapes and consistent bowl profiles differed from terrestrial volcanic calderas, which show more variety. In 1892, geologist Grove Carl Gilbert proposed that lunar craters formed by meteorite impacts, offering evidence including the circular shapes, ejecta blankets, and ray systems. However, few contemporaries accepted this idea, finding it difficult to believe such enormous impacts occurred frequently enough to cover the moon with craters. Not until the 1960s, after geologists better understood terrestrial impact craters and after the nuclear age provided analogies for explosive energy release, did the impact hypothesis become widely accepted. Eugene Shoemaker's systematic studies of Meteor Crater in Arizona and his comparison of nuclear test craters to lunar features helped establish impact cratering as the dominant process shaping the moon's surface. This realization transformed lunar science, making the moon's surface a historical record of the solar system's impact history. Before the space age, scientists could only speculate about lunar composition and conditions. Some believed the Maria might contain fine dust meters deep, potentially swallowing any spacecraft that landed. Others worried about sharp, rocky terrain that would damage landers. Temperature estimates suggested wild swings from scorching daytime heat to extreme nighttime cold. The moon's surface environment remained mysterious, with some details resolvable only by visiting directly. Understanding the moon's motion challenged astronomers for centuries. The moon doesn't orbit Earth in a simple ellipse. Its orbit precesses, the ellipse slowly rotates. The Moon's distance from Earth varies from 356,500 to 406,700 kilometers from perigee to apogee. Its orbital inclination, the tilt of its orbit relative to Earth's equator, changes over time. The Moon shows libration-slight rocking motions that allow observers on Earth to glimpse slightly more than half the lunar surface over time. Explaining all these motions required sophisticated celestial mechanics, contributing to the development of advanced mathematics. Newton's law of universal gravitation, published in 1687, provided the framework for understanding lunar motion. The Moon orbits Earth following the same gravitational law governing apple falling from trees, a profound unification of terrestrial and celestial phenomena. However, calculating precise lunar positions required accounting for perturbations from the Sun's gravity, Earth's non-spherical shape, and other effects. This three-body problem of calculating motions under mutual gravitational attractions proved mathematically intractable for exact solutions, requiring approximation techniques that drove mathematical innovation for centuries. By the early 20th century, astronomers could predict lunar positions with remarkable accuracy, important for navigation and eclipse predictions. They'd mapped the visible lunar surface in detail, identifying thousands of features. They'd measured the Moon's size, mass, density, and orbital parameters precisely. They understood lunar phases, eclipses, and the Moon's influence on tides. What remained mysterious was the Moon's interior, its detailed composition, its history, and whether it harboured any resources useful for future exploration. The space age would soon answer these questions, and many more, transforming the Moon from a distant object of astronomical study into a world that humans could visit, a place where we could walk and work, and eventually, perhaps live. The journey from telescopic observations to human footprints on lunar soil represents one of history's most dramatic technological achievements. Driven by Cold War competition, but resulting in scientific discoveries that transcended politics. The story of reaching the Moon involves thousands of people, multiple missions, both triumphs and tragedies, and ultimately redefined humanity's relationship with its celestial neighbour. The space race began not with the Moon as a goal, but with Earth orbit. On October 4th, 1957, the Soviet Union launched Sputnik 1, the first artificial satellite, shocking the United States and triggering an arms race and space competition. The geopolitical implications were profound. If the Soviets could launch satellites, they could launch intercontinental ballistic missiles capable of reaching American cities. The space race became a proxy for demonstrating technological superiority and ideological strength. The Soviets initially dominated this competition. They launched the first animal into orbit, Laika the dog, on Sputnik 2 in November 1957. They sent the first human into space, Yuri Gagarin, who orbited Earth on April 12, 1961, returning safely and becoming an international hero. These achievements embarrassed and alarmed American leaders who saw their nation's technological prestige declining. President John F. Kennedy, seeking a bold goal that could restore American confidence and demonstrate capability, seized upon a lunar landing. On May 25, 1961, just weeks after Gagarin's flight, and mere days after Alan Shepard became the first American in space on a brief, suborbital flight, Kennedy addressed Congress with a famous challenge. "I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the Moon and returning him safely to the Earth." This commitment was audacious. In 1961, the United States had barely achieved suborbital flight. No spacecraft had ever rendezvoused with another in orbit, a capability essential for lunar missions. No one had ever walked in space. Life support systems for extended missions didn't exist. Rockets powerful enough to send humans beyond Earth orbit remain purely conceptual. The technologies required for a lunar landing guidance computers, orbital mechanics calculations, spacesuits capable of operating on the lunar surface, all needed to be developed from scratch. NASA, the National Aeronautics and Space Administration, established in 1958 partly in response to Sputnik, received the challenge. The Apollo program began to take shape, requiring parallel development of multiple systems. The Saturn rocket family to provide launch capability, the Apollo spacecraft consisting of command, service, and lunar modules, spacesuits, training facilities, tracking stations, and more. At its peak, Apollo employed roughly 400,000 people across government, industry, and academia. Meanwhile, robotic missions paved the way. The Ranger program sent spacecraft crashing into the moon while transmitting images up until impact. Rangers 7, 8, and 9, launched between 1964 and 1965, returned thousands of photographs showing the lunar surface at increasing resolution, revealing that the moon's surface consisted of solid terrain, not treacherous dust, and providing data for selecting landing sites. The Surveyor program soft-landed spacecraft on the moon to test landing techniques and study surface conditions. Surveyor 1, landing successfully in June 1966, returned panoramic photographs and tested the surface's bearing strength. Subsequent surveyors analysed soil composition and proved that spacecraft could land safely on mere surfaces. Meanwhile, lunar orbiters photographed the moon from orbit at high resolution, mapping potential landing sites and creating the photographic foundation for Apollo planning. The Soviets pursued lunar goals as well. Their lunar program achieved multiple firsts. Luna 2 became the first spacecraft to reach the moon, impacting in September 1959. Luna 3 photographed the far side for the first time in October 1959. Luna 9 achieved the first soft landing in February 1966. The Soviets developed the enormous N-1 rocket to compete with America's Saturn V, planning to land cosmonauts on the moon and even researching a lunar base. However, technical problems plagued the N-1, with all 4 test launches ending in failure. After Apollo's success, the Soviet Union quietly abandoned lunar landing plans, though they continued robotic missions, including the successful Luna 16, 20, and 24 sample return missions. For the Apollo program, testing proceeded in stages. Mercury had proven humans could survive spaceflight. Gemini, a 2-seat spacecraft program running from 1965 to 1966, developed rendezvous and docking techniques, demonstrated spacewalks, and extended mission durations to 2 weeks. Each Gemini mission advanced capabilities needed for Apollo. The Apollo spacecraft itself consisted of 3 components. The command module housed the crew during most of the mission, providing life support, communications, and re-entry capability. The service module contained fuel cells, oxygen, water, the main engine, and other systems supporting the command module. The lunar module, spindly, fragile-looking craft, would carry 2 astronauts from lunar orbit to the surface and back. All 3 components together, along with the Saturn V rocket, constituted an integrated system of remarkable sophistication. The Saturn V rocket, designed by Wernher von Braun's team, stood 111 meters tall and weighed 2,800 metric tons fully fueled. Its first stage, powered by 5 F1 engines, burning kerosene and liquid oxygen, generated 34 meganewtons of thrust, still the most powerful rocket stage ever flown. The second stage used 5 J2 engines, burning liquid hydrogen and oxygen. The third stage, a single J2 engine, would propel the spacecraft toward the moon after achieving Earth orbit. The Saturn V's power and reliability proved crucial No Saturn V ever failed. Tragedy struck before Apollo could fly. On January 27, 1967, during a routine launchpad test of the Apollo 1 spacecraft, fire erupted in the pure oxygen atmosphere of the cabin. The fire spread instantly, fed by the high oxygen pressure and flammable materials. Astronauts Gus Grissom, Ed White, and Roger Chaffee died within minutes, unable to open the inward opening hatch against the pressure. The disaster shocked NASA and the nation, leading to extensive spacecraft redesigns, safety reviews, and a delay of nearly 2 years. When Apollo flights resumed with Apollo 7 in October 1968, an Earth orbital test of the command and service modules, NASA compressed the schedule to meet Kennedy's deadline. Apollo 8 in December 1968 made the dramatic decision to circle the Moon on only the second crewed Apollo flight, testing navigation and communications at lunar distance and providing humanity's first direct view of the far side. The crew's Christmas Eve broadcast, during which they read from the Book of Genesis while showing views of Earth rising above the lunar horizon, became one of the most watched television events in history. Apollo 9 in March 1969 tested the lunar module in Earth orbit, proving it could separate, maneuver independently, and redock with the command module. Apollo 10 in May 1969 descended to within 15 kilometers of the lunar surface during a full dress rehearsal of everything except landing itself. These methodical steps built confidence and validated systems and procedures. Then came Apollo 11. On July 16, 1969, Neil Armstrong, Buzz Aldrin and Michael Collins launched aboard Saturn V AS-506 from Kennedy Space Center in Florida. The world watched as the rocket climbed toward orbit, its roar echoing across the Florida marshland. 3 days later, after a mostly uneventful cruise, the spacecraft entered lunar orbit. Armstrong and Aldrin transferred to the lunar module, named Eagle, and separated from Columbia, the command module where Collins would remain in orbit. Eagle's descent began over the far side, out of communication with Earth. When radio contact resumed, controllers heard Armstrong calmly reporting milestones as Eagle descended. But as the landing site approached, Armstrong realized the computer was guiding them toward a boulder field within a large crater. He took manual control, flying Eagle over the rough terrain, while propellant gauges dropped toward empty. With perhaps 20 seconds of fuel remaining, he set Eagle down in a relatively smooth area. His understated words entered history. The Eagle has landed. 6.5 hours later, after checking systems and preparing equipment, Armstrong opened the hatch and climbed down Eagle's ladder. At 02:56 UTC on July 21, 1969, his left foot touched the lunar surface. His words, transmitted to hundreds of millions watching worldwide, captured the moment's significance. That's one small step for a man, one giant leap for mankind. Armstrong intended to say, a man, though the article is difficult to hear in the transmission. Aldrin joined him shortly after, and together they spent 2.5 hours outside, collecting samples, setting up experiments, including a seismometer and laser retroreflector, and taking photographs. They described the surface as fine-grained powder, easily kicked up, with a fragile crust. They found movement difficult in their pressurized suits but manageable. The stark landscape, with its black sky and harsh shadows, appeared both alien and strangely beautiful. After returning to Eagle and resting, they launched from the Moon using the ascent stage, leaving the descent stage behind as a permanent memorial. The ascent engine ignited successfully. There was no backup if it failed, and Eagle climbed back to orbit for rendezvous with Columbia. After docking and transferring to the command module, they jettisoned Eagle and began the return journey. On July 24th, Columbia splashed down in the Pacific Ocean, completing the mission and fulfilling Kennedy's goal with 5 months to spare. 5 more Apollo missions landed on the Moon, each building on previous successes and venturing to more challenging terrain. Apollo 12 in November 1969 demonstrated precision landing by touching down within walking distance of Surveyor 3, which had landed 2 years earlier. Astronauts. Pete Conrad and Alan Bean conducted 2 moonwalks, collected samples, and retrieved parts from Surveyor 3 for study of how materials weathered in the lunar environment. Apollo 13, launched in April 1970, never landed. An oxygen tank explosion crippled the service module while en route to the Moon, forcing the crew Jim Lovell, Jack Swigert, and Fred Hayes to abandon the mission and use the lunar module as a lifeboat. The world watched anxiously as NASA improvised solutions to bring the crew home safely. The successful return demonstrated NASA's capability to respond to emergencies and the importance of backup systems and procedures, though it highlighted the risks inherent in space exploration. Apollo 14 in February 1971 landed near Fra Mauro, the intended Apollo 13 destination. Alan Shepard, America's first astronaut, finally reached the Moon at age 47. He and Edgar Mitchell conducted experiments, collected samples from what they hoped was ejecta from the Imbrium Basin, and famously, Shepard hit golf balls on the lunar surface, demonstrating their flight in the 1/6 gravity environment. The final 3 Apollo missions, 15, 16 and 17, carried the lunar roving vehicle, a battery-powered car that extended exploration range and allowed collection of samples from diverse locations. Apollo 15 in July-August 1971 landed near Hadley Ryle, where David Scott and James Irwin collected samples, including the Genesis Rock, a piece of ancient lunar crust, 4.1 billion years old, among the oldest rocks returned from the Moon. Apollo 16, in April 1972, explored the Descartes Highlands, seeking volcanic rocks but finding only impact breccias, demonstrating that not all highland terrains are volcanic. John Young and Charles Duke conducted 3 moonwalks and drove the rover over 27 kilometers total. Apollo 17, in December 1972, was the final Apollo mission and the only one to include a professional scientist-geologist, Harrison Schmitt. The landing site, Taurus Littrow Valley, proved spectacularly interesting. Eugene Cernan and Schmitt discovered orange soil, actually ancient glass beads from volcanic eruptions, collected a variety of samples documenting lunar geological diversity, and conducted experiments, including detonating explosives, to study seismic wave propagation. When Cernan climbed back into the lunar module for the last time, his closing words acknowledged the achievement. "We leave as we came, and God willing, as we shall return, with peace and hope for all mankind." In total, 6 Apollo missions landed successfully, and 12 astronauts walked on the Moon. They spent a combined 80 hours on the lunar surface, traversed nearly 100 kilometers in rovers, and returned 382 kilograms of rocks and soil. They conducted experiments ranging from seismology to solar wind measurements to laser ranging. They planted American flags, left commemorative plaques, and positioned equipment that still returns data today. Why did Apollo end? Multiple factors contributed. The program's enormous cost, roughly $25 billion in 1960s dollars, equivalent to over $150 billion today, proved difficult to sustain once the primary goal was achieved. Public interest declined after initial missions. The Vietnam War and domestic social issues competed for attention and resources. The scientific community, while grateful for the samples and data, argued that robotic missions could accomplish much of Apollo's scientific goals at far lower cost and risk. 3 planned missions, Apollos 18, 19 and 20, were cancelled. Yet Apollo's legacy extends beyond the missions themselves. The technological developments, miniaturized computers, advanced materials, life support systems, communications technology found applications far beyond space exploration. The program demonstrated what focused effort and resources could achieve. The images of Earth from space, particularly Earthrise, photographed by Apollo 8, and the blue marble from Apollo 17, helped spawn the environmental movement by showing Earth as a fragile oasis in the void. The achievement remains unmatched. No human has ventured beyond low Earth orbit since Apollo 17. When the first lunar samples arrived on Earth in July 1969, scientists faced an unprecedented opportunity. Pristine rocks from another world, uncontaminated by Earth's atmosphere and biology, waiting to reveal the moon's secrets. The 21.6 kilograms returned by Apollo 11 represented merely the beginning. Subsequent missions brought back samples from diverse locations, each contributing pieces to the puzzle of lunar history. The total haul of 382 kilograms of rock, core samples, and regolith from 6 landing sites created a treasure trove that scientists continue studying today, more than 5 decades later. The samples reached Earth under strict contamination protocols. NASA built the Lunar Receiving Laboratory in Houston to quarantine returning astronauts and samples, protecting Earth from potential lunar pathogens, a possibility taken seriously despite its implausibility, and protecting samples from terrestrial contamination. The rocks were stored in nitrogen-filled cabinets, handled only with special tools, and distributed to researchers worldwide under careful controls. Initial examinations revealed fundamental characteristics. The rocks were bone dry, containing essentially no water compared to terrestrial rocks, confirming the moon's depleted volatile inventory. They lacked any signs of biological activity, no fossils, no organic molecules produced by life, no chemical signatures of biology. This wasn't surprising, given the moon's lack of atmosphere and water, but it definitively ruled out any possibility of lunar life. Age dating of the samples through radiometric techniques provided crucial timeline information. Radiometric dating relies on measuring ratios of radioactive isotopes and their decay products in minerals. Different isotope systems work for different age ranges and materials. For lunar rocks, uranium-lead, rubidium-strontium, and samarium-neodymium dating systems proved particularly useful. The oldest samples dated to around 4.4 billion years ago, placing their formation within the moon's first 150 million years. These ancient crustal rocks, including the Genesis rock from Apollo 15, represented pieces of the primordial lunar crust that solidified from the magma ocean. Their antiquity made them precious scientifically. Earth's crust has been so thoroughly recycled by plate tectonics that rocks older than 4 billion years are exceedingly rare. Yet the moon preserves samples from this early epoch in abundance. Mare basalt showed ages clustering between 3.2 and 3.9 billion years, though some samples proved younger. This confirmed that lunar volcanism occurred long after the crust formation, filling impact basins with lava hundreds of millions of years after the impacts themselves. The youngest Mare samples dated to around 1.2 billion years ago, indicating volcanic activity continued far longer than many scientists expected, though it was waning by then. The composition of Mare basalts revealed they originated deep in the lunar mantle. These basalts contained high levels of iron, magnesium, and titanium, but were depleted in sodium, potassium, and other volatile elements. Some basalts showed extreme titanium enrichment, containing over 10% titanium oxide, far higher than typical terrestrial basalts. The chemical variations between samples from different maria indicated they came from different source regions, or formed through different degrees of partial melting, providing insights into mantle structure and evolution. Highland rocks showed distinctly different compositions. Anorthosite rocks composed almost entirely of plagioclase feldspar dominated the highlands. Pure anorthosite is relatively rare on Earth, making these lunar rocks distinctive. Their formation through flotation of plagioclase crystals in a magma ocean provided strong support for the magma ocean hypothesis. The chemical signatures in highland rocks indicated they crystallized from a molten moon, capturing a snapshot of this dramatic early phase. Scientists also found rocks enriched in creep potassium, rare earth elements, and phosphorus. These elements concentrate in late-stage crystallization products, representing the last liquid as the magma ocean solidified. Creep-rich rocks provided insights into magma ocean differentiation and helped explain why the near side experienced more volcanism. The creep layer beneath the near side crust provided heat-producing radioactive elements that extended the period of mantle melting. Impact breccias made up a significant fraction of returned samples. These rocks consist of fragments of various rocks welded together by impact processes, melting, shock compression, or simple mechanical mixing. Some breccias contained fragments of older breccias, indicating the lunar surface has been reworked repeatedly. The complexity of breccia formation histories challenged researchers trying to decipher lunar geological processes, as individual fragments within a single breccia might have vastly different ages and origins. Tiny glass beads pervaded the lunar regolith. These beads formed when impact-melted droplets of rock splashed outward, cooling rapidly in flight or during landing. Their shapes perfect spheres if they cooled in flight, teardrop shapes if they cooled on impact told stories of their formation. Chemical analysis of the glass revealed the composition of source materials, effectively sampling small areas across the moon through splashing of impact melt. Orange glass beads discovered at the Apollo 17 site proved particularly interesting, indicating ancient volcanic eruptions of a type not directly observed elsewhere. The samples contained no minerals that require water for formation. On Earth, many minerals form in water-rich environments, clays, hydrated salts, serpentine, but lunar samples completely lacked such minerals. This reinforced the moon's dry nature. However, small amounts of water were detected in some samples, initially thought to be contamination, but later recognized as possibly indigenous. The water concentrations remained tiny parts per million or less, but raised questions about water sources and cycling on the moon. Solar wind particles embedded in lunar rocks provided another scientific windfall. The moon lacks a global magnetic field or atmosphere, so solar wind particles, mostly protons, and helium nuclei impact the surface directly and become implanted in rocks and regolith. By extracting and analysing these particles, scientists could study the sun's output over geological time. The ratio of helium-3 to helium-4 in solar wind, for instance, revealed information about nuclear processes in the sun's core. Cosmic ray tracks in lunar samples provided age information and exposure histories. Cosmic rays, high-energy particles from supernova explosions and other energetic processes strike the lunar surface continuously. When they pass through crystals, they damage the crystal lattice, leaving tracks visible under microscopes. Counting track densities allowed researchers to determine how long rocks had been exposed on the surface before being collected, helping understand regolith formation rates and surface processes. Some rocks contained shock features, planar deformation features, shatter cones, high-pressure mineral phases, indicating they experienced tremendous pressures during impacts. The presence of coesite and stishovite high-pressure, forms of quartz that don't occur naturally on Earth's surface, confirmed that impacts generate pressures exceeding hundreds of thousands of atmospheres. These shock features helped scientists understand impact mechanics and identify terrestrial impact craters, as similar features appear in rocks from Earth's impact sites. The Apollo samples also revealed the Moon's magnetic history. Some lunar rocks contain weak but measurable magnetization, implying they formed or cooled in the presence of a magnetic field. Since the Moon today lacks a global magnetic field, its core is too small and cool to generate one through dynamo action. This magnetization suggests the Moon possessed a field billions of years ago. Whether this field arose from an internal dynamo or from transient fields generated during major impacts remains debated. Micrometeorites and meteorite fragments found in the regolith provided samples of asteroids delivered conveniently to the Moon. These fragments, identified through their distinctive chemical and isotopic signatures, represent types of asteroids rarely sampled in our meteorite collections, as they're too fragile to survive atmospheric entry. The Moon essentially acts as a collection plate, accumulating meteorites that can be recovered and studied. The samples confirmed the Moon's differentiated interior structure. Seismometers placed by Apollo astronauts detected moonquakes, lunar earthquakes that revealed internal layering through seismic wave propagation. The data suggested a crust averaging 40 to 50 kilometers thick, a mantle extending down nearly 1,000 kilometers, and a small core perhaps 300-400 kilometers in radius. The core's composition remains uncertain, likely iron, possibly partially molten, but its small size compared to Earth's core reflects the Moon's overall iron depletion. Isotopic studies provided perhaps the most profound insights. Scientists measured isotopic ratios of oxygen, titanium, chromium, and other elements with high precision. These measurements showed Earth and Moon share nearly identical isotopic signatures, far more similar than any other solar system bodies we've sampled. This similarity strongly supports the giant impact hypothesis, as it suggests Earth and Moon formed from the same material or from materials that mixed thoroughly during the impact. Yet some puzzles remain. The extreme similarity in oxygen isotopes between Earth and Moon suggests mixing beyond what typical giant impact simulations produce. Either Theia happened to share Earth's oxygen isotopic composition possible if it formed nearby in the solar system, or the impact and subsequent disk evolution mixed materials more thoroughly than models predict. Recent high-precision measurements of other isotopes like tungsten and titanium have shown slight differences between Earth and Moon, complicating the picture but providing new constraints on impact models. The lack of water in Apollo samples was initially thought to prove the Moon completely dry, but subsequent analyses using more sensitive techniques detected water molecules bound in minerals and volcanic glass. These detections, combined with orbital observations of water in permanently shadowed craters and spectroscopic detections of OH molecules, have revised our understanding. The Moon isn't bone dry, but instead contains small amounts of water from various sources: comets, solar wind interactions, volcanic outgassing. Determining water abundance and distribution remains an active research area with implications for future lunar exploration. Soviet lunar sample return missions, though often overshadowed by Apollo, returned valuable samples from different locations. Luna 16, 20 and 24 collected a combined total of about 0.3 kilograms of regolith through automated drilling and return. These missions sampled Maria not visited by Apollo, extending our geographic coverage and confirming that Mare basalts show compositional variations across different regions. The success of automated sample return demonstrated alternative approaches to lunar exploration that might become important for future missions. Today, the Apollo samples remain scientifically productive. New analytical techniques allow measurements impossible in the 1970s. Researchers continue publishing papers based on these samples, extracting information about lunar formation, evolution, and resources. NASA carefully curates the collection, allocating samples to researchers worldwide while preserving material for future analyses. Some samples remain unopened, saved for future scientists with better tools and different questions. The samples transformed our understanding of the Moon from abstract theories to concrete evidence. They confirmed the Moon's great age, revealed its differentiation from a magma ocean, documented its volcanic history, demonstrated its bombardment record, and supported the giant impact formation hypothesis. Every lunar rock tells a story, and collectively they narrate 4.5 billion years of lunar history, a history intimately connected to Earth's own evolution. After Apollo 17's departure in December 1972, the Moon fell quiet. No spacecraft visited for more than 3 years, and no humans have returned in the 5 decades since. Yet the Moon never truly left scientific and political consciousness. As the 1990s approached, interest in lunar exploration experienced a renaissance driven by new technologies, international aspirations, and evolving scientific questions. The era of modern lunar exploration began, characterized by global participation, sophisticated instrumentation, and missions that transformed our understanding of Earth's companion. The United States returned first with Clementine, launched in January 1994. This modest spacecraft, developed by the Department of Defense partly as a technology demonstration for sensors that might detect ballistic missiles, carried cameras and spectrometers into lunar orbit. Over 2 months, Clementine mapped the entire Moon at multiple wavelengths, creating global datasets of unprecedented quality. The mission revealed the Moon's topography with new precision, identified compositional variations, and made an intriguing discovery. Radar data suggested possible water ice in permanently shadowed craters at the South Pole. Though later data complicated this interpretation, Clementine reinvigorated lunar exploration by showing what relatively inexpensive missions could accomplish. Lunar Prospector followed in January 1998, carrying instruments to measure the Moon's composition, gravity, and magnetic fields. The neutron spectrometer provided crucial data about hydrogen concentrations, which could indicate water ice deposits. Lunar Prospector confirmed elevated hydrogen levels at both poles, consistent with water ice in permanently shadowed regions. The spacecraft also mapped the Moon's weak magnetic field, revealing anomalies that might represent remnant crustal magnetization from ancient impacts. At mission's end, Lunar Prospector deliberately crashed into a permanently shadowed crater, with observers watching for vapor plumes that might indicate ice, though none were detected definitively. Europe entered lunar exploration with SMART 1, launched in September 2003. This technology demonstration mission tested an ion propulsion engine electric thrusters, providing gentle but continuous acceleration for deep space applications. SMART 1 reached the Moon using this efficient propulsion, then conducted scientific observations, including spectroscopic mapping of mineral compositions and searches for calcium-rich highland rocks. Though modest in scientific scope, SMART 1 demonstrated technologies and established European capabilities for lunar missions. Japan's Kaguya mission, launched in September 2007, represented the most sophisticated lunar orbiter since Apollo. Carrying 13 instruments, including high-definition cameras, spectrometers, radar, and a gravity-measuring sub-satellite, Kaguya spent nearly 2 years mapping the Moon comprehensively. The mission returned stunning high-definition videos of lunar terrain, including dramatic footage of Earth rising over the lunar horizon. Kaguya's gravity measurements revealed subtle variations indicating crustal thickness differences and potential mass concentrations beneath impact basins. The mission demonstrated Japan's growing capabilities and provided data still being analysed today. China entered lunar exploration with impressive focus and persistence. Chang'e 1, launched in October 2007, orbited the moon mapping surface composition and topography. Chang'e 2, launched in 2010, provided higher resolution imaging and gravity measurements. Then, in December 2013, Chang'e 3 achieved China's first lunar landing, touching down in Mare Imbrium. The lander carried instruments for soil analysis and astronomical observations, while the U2 rover explored the surrounding terrain, analysing rocks and subsurface structure with ground-penetrating radar. Though U2 experienced mechanical problems that limited mobility, the mission succeeded magnificently, making China the third nation to soft land on the moon. India's Chandrayaan-1, launched in October 2008, made history by definitively confirming water molecules on the lunar surface. The moon mineralogy mapper provided by NASA detected spectral signatures of water and hydroxyl molecules in sunlit areas across the moon, particularly at high latitudes. This discovery revolutionized our understanding. The moon wasn't bone dry, but instead possessed water distributed more widely than previously thought. The findings suggested ongoing processes where solar wind protons interact with oxygen in lunar minerals to form water molecules, though the detailed mechanisms and variations remain under investigation. NASA's Lunar Reconnaissance Orbiter, LRO, launched in June 2009, continues operating today as the longest-lived lunar orbiter. LRO's suite of instruments provides extraordinary detail, cameras resolving features smaller than a metre, allowing identification of Apollo landing sites, including tracks left by rovers and astronauts. A laser altimeter measuring topography with unprecedented precision, creating elevation maps revealing subtle features. A neutron detector mapping hydrogen concentrations indicative of water ice. A temperature instrument measuring thermal emissions to identify cold traps where volatiles might accumulate. And a cosmic ray detector studying the radiation environment crucial for human exploration planning. LRO confirmed water ice in permanently shadowed craters, identified hundreds of pits that might offer cave entrances providing natural shelter, discovered that surface temperatures in permanently shadowed craters reach below 40 Kelvin, cold enough to trap even volatile gases like carbon dioxide, and documented the lunar environment in detail, supporting future exploration. LRO continues returning data, with its extended mission now outlasting its planned duration many times over. China's Chang'e 4, launched in December 2018, achieved something unprecedented, landing on the lunar far side. Because the far side never faces Earth, direct communication is impossible. China solved this by first launching a relay satellite, Kuekiao, to a special orbit beyond the Moon, where it can see both the far side and Earth simultaneously. Then, in January 2019, Chang'e 4 landed in von Karman crater, within the South Pole Aitken Basin. The mission deployed the U-22 rover, which has travelled over 1 kilometre, far exceeding its design life, and studied the local geology, including excavated material, possibly from deep in the crust or mantle. Chang'e 5, launched in November 2020, marked China's first sample return mission. Landing in Oceanus Procellarum, the mission collected about 1.7 kilograms of rock and regolith, then successfully returned them to Earth in December 2020. These samples came from a younger basaltic region than any Apollo samples, dating to about 2 billion years ago, based on initial analyses, extending our knowledge of lunar volcanism to more recent epochs. The success demonstrated China's growing sophistication and set the stage for future ambitious missions. India's Chandrayaan-2, launched in July 2019, attempted a landing near the South Pole, but unfortunately, the lander crashed during final descent. However, the orbiter portion continues operating successfully, conducting scientific observations, including detailed mapping of polar regions searching for water ice deposits. India's Chandrayaan-3, launched in July 2023, successfully landed near the South Pole in August 2023, making India the fourth country to soft land on the Moon and the first to land near the lunar South Pole. The lander and rover conducted experiments studying the polar environment and searching for water ice. South Korea entered lunar exploration with Danuri, launched in August 2022, which entered lunar orbit in December 2022. The mission carries cameras, a magnetometer, and a NASA-provided instrument for mapping water ice distribution. South Korea's participation represents the expanding international character of lunar exploration, with more nations developing capabilities. Private companies have joined the endeavour. Israel's Space IL attempted a landing in April 2019, but Bereshit crashed during descent due to technical failures. Japan's ISpace attempted a landing in April 2023, but also crashed. The United States' Robotic attempted a landing in January 2024, but a propellant leak forced abandoning the landing attempt. These attempts, though unsuccessful, demonstrate growing private sector capabilities and the challenges of lunar landing. Success in these commercial lunar landing programs could dramatically reduce costs and enable new exploration paradigms. Meanwhile, robotic missions have revealed the Moon's complexity. Measurements of water distribution show higher concentrations in permanently shadowed regions, but also detection of water molecules in sunlit areas, suggesting dynamic processes of formation, migration, and loss. Some water might be bound in minerals, while some might be mobile, migrating across the surface or through subsurface layers. Understanding water behaviour will be crucial for utilising this resource. Studies of lunar swirls. Strange bright markings on the surface associated with magnetic anomalies have proposed they form when magnetic fields deflect solar wind, protecting those areas from space weathering and keeping them brighter than surroundings. However, the exact mechanisms remain debated, with alternative hypotheses involving cometary impacts or dust electrostatic levitation. Observations of transient lunar phenomena. Brief glows or obscurations reported by observers throughout history have been attributed to outgassing events, electrostatically levitated dust, or observation artifacts. Some regions, particularly the crater Aristarchus, seem prone to these events, suggesting localized processes releasing gas or disturbing dust. Whether significant outgassing still occurs remains uncertain, but if it does, it indicates the Moon retains some internal activity despite its apparent geological death. Measurements of the lunar exosphere. The incredibly tenuous atmosphere, so thin it's essentially a vacuum but not quite, have detected sodium, potassium, helium, argon, and other species at concentrations trillions of times lower than Earth's atmosphere. These atoms come from solar wind sputtering, radioactive decay, and meteoroid impacts vaporizing surface material. The exosphere varies with solar activity, meteoroid flux, and location, creating a dynamic envelope despite its extreme tenuousness. The modern era has also seen renewed interest in lunar resources. Water ice, confirmed in polar regions, could provide drinking water, oxygen for breathing, and hydrogen and oxygen for rocket fuel through electrolysis, reducing the need to transport these materials from Earth. Helium-3, a rare isotope on Earth but relatively abundant in lunar regolith due to solar wind implantation, has been proposed as a potential fusion fuel, though fusion power using helium-3 remains technologically distant. Rare earth elements and metals could be extracted, though the economics remain uncertain given transportation costs. Most importantly, modern missions have prepared the ground, sometimes literally, for humanity's return. High-resolution images identify safe landing sites and traverse routes. Compositional maps locate resources. Radiation measurements quantify hazards astronauts will face. Topographic data enable precise landing navigation. Temperature measurements identify thermal environments for equipment design. Each mission adds pieces to our understanding, reducing unknowns and risks for future human exploration. The collective international effort United States, China, India, Japan, Europe, Russia, South Korea, and private entities reflects the Moon's universal appeal. Unlike the Cold War competition that drove Apollo, modern lunar exploration involves collaboration alongside competition, data sharing alongside proprietary missions, and scientific discovery alongside nationalistic pride. The Moon has become a proving ground for international cooperation in space, a laboratory for developing technologies, and the next frontier for human expansion beyond Earth. Standing on the lunar surface, an astronaut faces one of the most extreme environments in the solar system. The Moon lacks almost everything that makes Earth habitable: no atmosphere, no magnetic field, no liquid water, no protection from radiation. Yet understanding this environment fascinates scientists and engineers alike, as it represents the baseline conditions humans must overcome to explore space, and it preserves a record of processes operating throughout the solar system. The absence of atmosphere dominates many lunar characteristics. With no air to scatter sunlight, the sky remains pitch black even during daytime, with stars visible alongside the sun, a surreal sight for Apollo astronauts accustomed to Earth's blue skies. Shadows are absolutely black, illuminated only by light reflecting off nearby terrain or Earth, creating stark contrasts between sunlit areas and shadows that challenged photographers seeking balanced exposures. Without atmospheric pressure, the lunar surface exists in an ultra-high vacuum, with pressures around 1/1,000,000,000th of Earth's sea level pressure. At such pressures, water ice sublimes directly from solid to vapour. Liquids boil instantly, and exposed materials don't oxidize or weather through atmospheric chemical reactions. This vacuum preserves ancient surfaces. Rocks, dated to billions of years ago, sit exposed, showing impact craters and features formed when they first arrived at the surface, essentially unchanged except by micrometeorite impacts and radiation damage. Temperature extremes result from the lack of atmospheric heat distribution and the Moon's slow rotation. Lunar day and night each last about 14 Earth days. During the lunar day, surface temperatures in equatorial regions climb above 120 degrees Celsius hot, enough to boil water at Earth pressures, though water couldn't exist as liquid on the Moon. This heating is intense because no atmosphere moderates it, with sunlight delivering its full energy directly to the surface. Dark rocks absorb heat more efficiently than bright ones, creating localized temperature variations. During the lunar night, temperatures plunge toward minus 170 degrees Celsius near the equator, colder at high latitudes. Heat radiates away to space, with no atmosphere to trap it, and the 14-day night provides ample time for surfaces to cool completely. This temperature swing exceeds 250 degrees Celsius far beyond what any terrestrial environment experiences. Materials must withstand these cycles without cracking, warping, or failing, challenging engineers designing equipment for lunar exploration. The polar regions experience different conditions. Near the poles, the sun never rises far above the horizon even during lunar day, grazing terrain at shallow angles. Some crater rims receive nearly continuous illumination, peaks of eternal light, experiencing sunlit conditions almost continuously. Conversely, deep craters near the poles contain permanently shadowed regions where sunlight hasn't reached for billions of years. These permanently shadowed regions maintain temperatures below 40 Kelvin, cold enough that even volatile species like water ice, carbon dioxide, methane, and ammonia remain frozen indefinitely. These cold traps have accumulated volatiles over geological time. Water molecules, released through comet impacts, meteoroid vaporization, or chemical reactions, migrate across the lunar surface until reaching these permanent shadows, where they freeze and remain trapped. Over billions of years, this process has created deposits potentially containing millions of tons of water ice mixed with regolith, though the exact concentrations and distributions remain uncertain pending direct sampling. The moon's surface material regolith poses unique challenges. Pulverized by billions of years of meteoroid impacts, the regolith consists of fine particles ranging from dust to centimeter-sized fragments. Its texture resembles flour or powder, easily disturbed and kicked up by walking or rover wheels. The finest particles, micrometers in size, adhere to everything through electrostatic attraction, infiltrating equipment seals, coating solar panels, and abrading moving parts. Apollo astronauts reported dust as one of their biggest challenges, with suits becoming grey despite attempts to brush dust off before re-entering lunar modules. The regolith's low thermal conductivity, it's an excellent insulator, creates temperature gradients. Surface temperatures swing wildly, but just tens of centimeters below, temperatures remain relatively stable, suggesting subsurface environments might be easier to thermally control than surface habitats. Engineers designing lunar bases consider placing structures partially underground or covering them with regolith to provide insulation and radiation shielding. Radiation represents perhaps the most serious challenge for lunar exploration. Earth's magnetic field deflects charged particles, protons and electrons in the solar wind, preventing them from reaching the surface. Earth's atmosphere provides additional shielding, absorbing high-energy particles and electromagnetic radiation. The moon possesses neither protection. Solar wind particles impact the surface directly, as do galactic cosmic rays, high-energy atomic nuclei from supernovas and other sources outside the solar system. Solar flares can release enormous bursts of energetic particles, creating dangerous radiation levels within minutes. Astronauts on the moon face accumulated radiation doses far exceeding those in low Earth orbit, where Earth's magnetic field provides some protection. Long-duration stays on the moon require shielding, thick walls of regolith or water, underground habitats, or other protection to keep radiation exposure within acceptable limits. Solar flare warnings could require astronauts to shelter in protected areas until particle storms pass. Radiation damage to electronics also concerns mission planners, requiring hardened systems or replaceable components. The moon's weak gravity, 1/6 of Earth's, affects everything from walking to engineering. Apollo astronauts discovered bouncing in low arcs proved more efficient than walking for moving quickly. Objects fall slowly enough that catching dropped items becomes easier, though the low gravity also means objects thrown or kicked travel far. Dust particles kicked up by walking or rovers follow ballistic arcs, lacking air resistance to slow them, and can travel considerable distances before settling, potentially contaminating distant equipment. Low gravity simplifies launching spacecraft escape velocity from the Moon is only 2.4 kilometers per second compared to Earth's 11.2, meaning rockets can be much smaller and simpler. However, low gravity complicates some engineering fluid behavior in tanks differs, requiring special baffles or surface tension devices to ensure propellants reach pump inlets. Human physiology adapted to Earth gravity may experience bone loss and muscle atrophy during long stays, though the 1/6 gravity may cause these problems more slowly than the microgravity of orbit. The Moon lacks a global magnetic field, but possesses localized magnetic anomalies regions where crustal rocks remain magnetized from ancient times. These anomalies reach hundreds of nanoteslas in strength, weak compared to Earth's 50,000 nanotesla field, but measurable and significant for scientific studies. The anomalies might represent remnant magnetization from an ancient global field, or magnetization from massive impacts, which can generate transient, intense magnetic fields. Maps of these anomalies help scientists understand lunar magnetic history and impact processes. Moonquakes provide information about internal structure. Unlike Earth's plate tectonic earthquakes, moonquakes include deep events occurring about 700–1,000 kilometers deep, thought to arise from tidal stresses as Earth's gravity flexes the Moon. These deep moonquakes occur regularly, clustered at specific locations and times in the lunar orbit, demonstrating ongoing tidal deformation. Shallow moonquakes, rarer and occurring near the surface, might result from thermal stresses as surfaces heat and cool, or from impacts. Thermal moonquakes, tiny quakes from thermal expansion and contraction, occur regularly at sunrise and sunset. Meteorite impact moonquakes occur randomly when sizable meteoroids strike. The seismic characteristics of the Moon differ dramatically from Earth. Lacking water and with a highly fractured crust, the Moon transmits seismic waves differently. Seismic signals ring for extended periods. Apollo seismometers recorded moonquakes continuing for over an hour, whereas equivalent earthquakes last minutes at most. This prolonged ringing results from the Moon's dry, fractured structure, allowing waves to propagate longer without damping. Analysis of seismic wave speeds and paths has revealed the Moon's internal structure, including its crust, mantle, and small core. Meteoroid impacts continue today, though at far reduced rates compared to the Moon's early history. Small particles, micrometeoroids weighing fractions of grams, strike constantly, thousands per day, across the entire Moon. These impacts contribute to space weathering, gradually darkening and chemically altering surface materials. Larger impacts occur rarely, but remain observable. Bright flashes from impacts have been recorded by telescopes on Earth, particularly during meteor showers, when Earth and Moon pass through debris streams left by comets. These impacts can excavate craters meters across, ejecting material that slowly settles elsewhere. The lunar ionosphere and exosphere, though incredibly tenuous, still produce observable effects. Atoms and ions interact with solar wind, magnetic fields, and sunlight. Sodium atoms released from the surface form a tenuous sodium cloud extending thousands of kilometers above the Moon. Argon-40, produced by radioactive decay of potassium-40 in lunar rocks, slowly escapes from the interior and appears in the exosphere. These trace gases provide information about ongoing lunar processes and the balance between sources and losses of atmospheric species. Electric fields on the lunar surface arise from interactions between solar wind plasma, solar ultraviolet light ionizing surface atoms, and the photoelectric effect releasing electrons from sunlit surfaces. These fields, though weak by terrestrial standards, can levitate dust particles through electrostatic forces. Some researchers suggest electrostatic dust levitation explains transient observations of glows or obscurations in certain lunar locations, particularly near terminator regions where lighting transitions from day to night create complex charging conditions. However, the importance of dust levitation remains debated, with some scientists questioning whether electrostatic forces are strong enough to significantly affect dust distribution. The Moon crosses Earth's magnetosphere once per month, spending several days shielded from direct solar wind by Earth's magnetic field. During these periods, the lunar environment changes, solar wind bombardment ceases, charged particle fluxes drop, and the Moon experiences the complex plasma environment of Earth's magnetotail. Some researchers study these monthly variations to separate effects of solar wind impact from other space weathering processes. Humans have operated in this environment only briefly. The longest single stay was Apollo 17's 75 hours on the surface. Future missions will extend durations, requiring detailed understanding of how equipment and people cope with the extremes. The lunar environment, though hostile, is not insurmountable. With appropriate engineering thermal control, radiation shielding, dust management, life support, humans can not only visit but potentially live on the Moon, exploiting its unique characteristics for science, resource utilization, and as a stepping stone to deeper space exploration. The discovery of water on the Moon ranks among the most significant findings of recent lunar exploration, transforming our understanding of the Moon's chemistry and revolutionizing plans for future exploration. For decades following Apollo, the Moon was considered bone dry, with sample analyses showing water concentrations millions of times lower than terrestrial rocks. This apparent aridity shaped thinking about lunar formation and evolution. The giant impact's heat would have vaporized volatiles, and the Moon's low gravity and lack of atmosphere prevented retaining any atmosphere that might have formed. Water simply couldn't exist on such a hostile world. This paradigm began shifting in the 1990s. Clementine's radar data hinted at ice in polar craters. Lunar Prospector's neutron spectrometer detected elevated hydrogen at both poles, suggesting water ice concentrations of perhaps 1 to 2% mixed with regolith in permanently shadowed craters. However, skeptics noted hydrogen could come from solar wind implantation rather than water ice, and the indirect nature of neutron data allowed alternative interpretations. Definitive confirmation came from multiple sources. India's Chandrayaan-1 mission, through its Moon Mineralogy Mapper instrument, detected spectral signatures of water and hydroxyl molecules across the sunlit lunar surface in 2009. This detection surprised everyone. Not only did water exist, but it appeared in sunlit areas where temperatures should cause rapid sublimation. The discovery suggested ongoing processes were creating or replenishing water molecules faster than they were lost. The mechanism appears to involve solar wind protons, hydrogen, nuclei striking oxygen atoms in lunar minerals and bonding to form hydroxyl, OH, or water, H2O molecules. This process occurs continuously wherever sunlight hits the surface, though the water molecules remain bound to minerals or migrate quickly until finding cold traps. The concentration is low, perhaps hundreds of parts per million, but distributed globally, suggesting the lunar surface is a dynamic environment where water molecules form, break apart, migrate, and sometimes become trapped. NASA's L-CROSS mission provided more direct evidence of water ice. In October 2009, L-CROSS intentionally crashed into Cabeus crater near the South Pole, with a companion spacecraft flying through the resulting debris plume to analyze its composition. Instruments detected water vapor, ice, and various volatile compounds, including carbon dioxide, methane, ammonia, and others. The impact excavated material from permanently shadowed crater floors, providing the first direct sampling of these cold trap deposits. The water concentration in the excavated material reached approximately 5 to 6%, by mass far higher than expected and sufficient to potentially support future exploration. Subsequent missions have refined our understanding. The Lunar Reconnaissance Orbiter's neutron detector mapped hydrogen concentrations with higher resolution, identifying specific craters likely to contain elevated water ice. Temperature measurements confirmed that permanently shadowed regions maintain temperatures below 40 Kelvin year-round, cold enough to trap even relatively volatile species for billions of years. These ultra-cold regions, called cold traps, cover thousands of square kilometers at both poles. The distribution of water ice appears patchy and variable. Some permanently shadowed craters show strong hydrogen signatures suggesting substantial ice deposits, while others show weaker signatures despite similar temperatures. This variability might reflect differences in impact histories, with some craters having received more cometary impacts or more efficient volatile trapping. Alternatively, local topography and regolith properties might affect how volatiles migrate and accumulate. The source of lunar water likely includes multiple contributors. Comets, composed largely of water ice, have impacted the Moon throughout its history. Each cometary impact delivers millions to billions of tons of water, most of which would quickly sublime and escape, but some fraction might reach cold traps and become permanently stored. Asteroids, particularly carbonaceous types, also contain hydrated minerals that could release water upon impact. Solar wind represents another important source. The continuous flux of protons generates hydroxyl and water through chemical reactions with minerals, a process that has operated for billions of years. While individual water molecules formed this way might not survive long in sunlit regions, the cumulative production over geological timescales could be significant, especially if a fraction of produced molecules migrate to cold traps before being lost to space. Volcanic outgassing may have contributed water in the ancient past when lunar volcanism was active. Although mare basalts appear extremely dry, tiny glass beads from volcanic fire fountains contain traces of water and other volatiles, indicating the magmas that erupted retained small amounts despite extensive degassing. If volcanic eruptions released water vapor, some might have migrated to poles and been trapped, creating a reservoir of ancient volcanic water. The stability of water ice in permanently shadowed regions depends on temperature and the balance between delivery and loss mechanisms. At temperatures below 40 Kelvin, water ice sublimation rates become negligible. A deposit could remain stable for the age of the solar system. However, even in permanent shadow, some loss mechanisms operate. Micrometeorite impacts might vaporize ice, releasing water molecules that either recondense nearby or escape. Sputtering by energetic particles could erode ice over time. The observation that ice appears to exist in these regions despite these loss mechanisms suggests delivery rates have exceeded loss rates over geological time. Beyond water, other volatiles interest researchers. Carbon compounds detected by L-cross-methane, carbon monoxide, carbon dioxide might be useful for various applications. Ammonia could provide nitrogen, an essential element for biology. Noble gases like argon and helium offer insights into lunar history. Sulfur compounds detected in polar regions might indicate complex chemistry in cold trap environments. Understanding the inventory of volatiles will require direct sampling through drilling or excavation. The resource potential of lunar water excites planners of future missions. Water, broken down through electrolysis into hydrogen and oxygen, provides rocket propellant. Oxygen also supports human breathing. Water itself is necessary for drinking, hygiene, and agriculture. Transporting water from Earth costs thousands of dollars per kilogram. Finding it on the moon would dramatically reduce logistics costs for sustained exploration. However, extracting lunar water faces challenges. The water exists mixed with regolith at relatively low concentrations, requiring processing large volumes of material. The regolith must be heated to release water molecules, then the water vapor must be captured and condensed. This process requires energy sunlight via solar panels or nuclear reactors and equipment capable of operating in extreme cold and vacuum. The economics depend on concentration, extraction efficiency, and transportation costs factors still being studied. Some engineers propose mining permanently shadowed craters using remotely operated equipment, heating regolith and collecting released water vapor. Others suggest processing regolith in mobile smelters that move through illuminated areas or positioning processing plants at crater rims where they can access both ice in shadows and solar power in sunlight. Various methods are being studied, with none yet proven at operational scales. Beyond water, the moon offers other potential resources. Regolith contains metals iron, titanium, aluminum that could be extracted and used for construction. The lack of atmosphere and low gravity simplifies certain industrial processes that require vacuum or would benefit from reduced gravity. Helium-3, implanted by solar wind and concentrated relative to Earth, has been proposed as a potential fusion fuel. Though fusion power technology remains far from commercial viability, and helium-3 concentrations are low enough that enormous quantities of regolith would need processing. Rare earth elements and other valuable materials exist in lunar rocks, but whether extraction makes economic sense depends on prices, extraction costs, and transportation expenses. Unless these materials can be used on the moon or transportation costs drop dramatically, shipping them to Earth would be prohibitively expensive. However, materials used on the moon for construction, manufacturing, radiation shielding need not be transported, making in situ resource utilization attractive regardless of Earth markets. The lunar poles offer combinations of resources and environmental conditions that make them particularly attractive for bases. Water ice in nearby cold traps provides resources. Peaks of eternal light offer nearly continuous solar power, eliminating the challenge of surviving 14-day-long nights that equatorial bases would face. Moderate temperatures at poles warmer than shadows, cooler than equatorial days thermal control challenges. These factors make polar sites the focus of many near-term exploration plans. Understanding lunar resources requires continued exploration. Orbital measurements provide global perspectives, but limited detail. Robotic landers and rovers can study specific sites in detail, but cover limited areas. Human explorers could investigate large regions using mobility and judgment to identify promising areas and collect diverse samples. Future missions will likely combine these approaches: orbital reconnaissance, robotic prospecting, human evaluation, to characterize resources comprehensively. The presence of water on the moon doesn't just serve practical purposes, it also informs science. Water's sources, distribution, and preservation reveal processes operating throughout the inner solar system. Other airless bodies, Mercury, asteroids, moons of Mars might have similar cold trap deposits. Understanding water behavior on the moon provides insights applicable elsewhere. The discovery that the dry moon actually contains water in various forms and locations reminds us that space continues surprising us, that assumptions based on limited data can mislead and that careful observation and analysis reveal unexpected complexity even in familiar places. As we look forward from the current moment of renewed lunar interest, the Moon appears poised to experience activity unlike anything since Apollo. Multiple nations are planning ambitious missions, private companies are developing commercial lunar services, and serious proposals for permanent lunar bases are being refined. The coming decades may see the Moon transform from a destination occasionally visited by robots to a location where humans live and work continuously. Understanding these plans requires examining who plans to go, why, and what challenges must be overcome. The Artemis program represents NASA's current lunar architecture. Named after Apollo's twin sister in Greek mythology, Artemis aims to return humans to the Moon by the mid-2020s, establish sustained presence by the 2030s, and use the Moon as a proving ground for Mars exploration. Unlike Apollo's brief visits, Artemis envisions continuous exploration with infrastructure supporting multiple missions per year, growing in scope and capability over time. Artemis uses the Space Launch System, a heavy-lift rocket more powerful than the Saturn V to launch the Orion spacecraft carrying astronauts. Orion can support crews of 4 for missions lasting weeks, providing life support, communications, and re-entry capability. For lunar landing, Artemis will use commercial landers developed by private companies, with SpaceX's Starship selected as the initial system. This public-private partnership approach differs from Apollo's purely governmental structure, aiming to reduce costs and foster commercial lunar economy. A key Artemis element is Gateway, a small space station in a special orbit around the Moon called a near-rectilinear halo orbit. This orbit provides continuous communication with Earth and periodic close passes over the lunar South Pole, facilitating polar exploration. Gateway will serve as a staging point for lunar landings, a long-duration laboratory for testing life support and other systems, and potentially a stopping point for Mars missions. Gateway's first elements are scheduled for launch in the mid-2020s, with assembly continuing over subsequent years. Artemis missions will focus initially on the lunar South Pole. Artemis II, currently planned for the mid-2020s, will fly crew around the Moon without landing, testing systems and procedures. Artemis III aims to land astronauts on the Moon, including the first woman and first person of colour on the lunar surface, at a South Polar site selected for resource potential and scientific interest. Subsequent missions will establish greater infrastructure, with goals including a lunar terrain vehicle for extended traverses, a habitation module for longer surface stays, and power systems supporting sustained operations. The scientific objectives for Artemis are ambitious. Collecting samples from diverse geological units will constrain the Moon's magma ocean evolution and differentiation. Studying permanently shadowed regions will reveal volatile accumulation processes and test resource extraction technologies. Deploying seismometers will constrain interior structure with better coverage than Apollo's network provided. Conducting astronomy from the Moon, particularly radio astronomy on the far side, shielded from Earth's radio interference, could enable observations impossible from Earth or space-based observatories. China's lunar program proceeds aggressively and with clear long-term vision. Following the Chang'e 4 far-side landing and Chang'e 5 sample return, China plans Chang'e 6 to return samples from the far side, Chang'e 7 to explore the South Pole, searching for water ice and resources, and Chang'e 8 to test in-situ resource utilization technologies. Beyond these robotic missions, China has announced plans for human lunar landings by the 2030s, with infrastructure supporting sustained presence and eventual lunar base construction. China's stated goals include scientific research, resource exploitation, and demonstrating technological capability. Russia and China have announced plans to collaborate on an international lunar research station, envisioning robotic and human operations initially at the lunar South Pole, expanding to other locations over time. Details remain general, but the partnership represents Russia's shift away from collaboration with the United States and Europe toward partnership with China in space exploration. How this program develops depends on geopolitical factors and technical progress by both nations. India continues developing lunar capabilities following Chandrayaan-3's success. Plans include sample return missions, potential human missions using developing Indian rockets and spacecraft, and participation in international lunar exploration efforts. Japan also pursues lunar ambitions, with robotic landers and rovers planned and eventual human participation possible through partnership with the United States via Artemis agreements. Europe's role in lunar exploration involves both independent projects and partnerships. European industry is building gateway modules and providing service modules for Orion spacecraft. The European Space Agency studies concepts for lunar landers and habitats. European astronauts will likely participate in Artemis missions, continuing decades of US-European cooperation in human spaceflight. However, Europe's space budget is smaller relative to the United States or China, limiting independent capability while ensuring continued involvement through partnerships. Commercial entities are developing lunar capabilities with varying business models. Historically, space exploration was dominated by governments, but decreasing launch costs and improving technologies have enabled private sector participation. Companies developing lunar landers, rovers, communication systems, and services hope to create profitable businesses supporting government exploration while enabling commercial activities. Astrobotic, Intuitive Machines, and others are developing landers capable of delivering payloads to the lunar surface at costs dramatically below historical government missions. These companies envision regular cargo flights, transporting instruments, equipment, and supplies for customers ranging from governments to universities to private entities. If successful, such services could enable lunar activities previously too expensive to consider frequent scientific missions, resource prospecting, testing technologies, even entertainment and tourism ventures. SpaceX's Starship system, selected by NASA for Artemis landings, represents potentially revolutionary capability if it reaches full operational status. Starship is designed to be fully reusable, launch frequently, and carry large payloads, potentially over 100 tons, to the lunar surface. Such capability would transform lunar exploration, making large-scale infrastructure construction feasible. SpaceX's founder has stated goals of eventually making the Moon and Mars accessible for permanent settlement, with Starship as the transportation system enabling this vision. Mining companies are examining lunar resource potential. Extracting water ice for propellant could enable refueling depots supporting deep space exploration. Processing regolith for metals might support lunar construction. Some companies propose extracting rare materials for return to Earth, though the economics remain speculative. Whether commercial lunar mining becomes viable depends on technological development, cost reduction, and market demand uncertainties that will only resolve over coming decades. Tourism represents another commercial possibility. Several companies propose lunar tourism, initially flyby missions without landing, eventually surface visits. The market likely consists of extremely wealthy individuals willing to pay millions for the experience. Whether such tourism becomes routine depends on cost reduction and safety improvements, as well as whether sufficient wealthy customers exist to support a sustainable industry. The challenges facing lunar exploration and settlement are formidable. The technical requirements, reliable transportation, life support, power, construction, resource processing remain expensive and partly unproven. The physiological effects of prolonged lunar gravity exposure on humans remain unknown. Will 1/6 gravity prevent bone loss and muscle atrophy, or merely slow these problems? The psychological challenges of isolation, confinement, and danger could affect crew performance and mental health. Radiation exposure during extended stays might exceed safe limits without substantial shielding. Legal and political frameworks for lunar activity remain underdeveloped. The Outer Space Treaty of 1967 establishes that no nation can claim sovereignty over the Moon, that space exploration should benefit all humanity, and that nations are responsible for their space activities. However, the treaty doesn't clearly address resource extraction, property rights, or commercial activities. The Artemis Accords, signed by multiple nations partnering with the United States, attempt to establish norms for peaceful lunar exploration, including transparency, interoperability, and resource extraction guidelines. But not all spacefaring nations have signed, raising questions about international consensus. Resource utilization raises philosophical and ethical questions. Should lunar resources be exploited? Who benefits? Only wealthy nations and companies with capability to access them, or all humanity? Should pristine areas be preserved for scientific study? Should culturally significant sites like Apollo landing locations be protected? These questions have no easy answers, but will become increasingly urgent as capability to affect the Moon increases. Environmental considerations arise as well. The Moon lacks life, so biological contamination isn't a concern, but human activities could affect scientific investigations. Lunar bases will generate waste. What happens to it? Mining operations could alter terrain, potentially destroying evidence of geological or impact history. Communications installations could interfere with radio astronomy. Balancing exploration goals with environmental stewardship will require careful planning and international coordination. Despite challenges, compelling reasons exist for lunar exploration and settlement. Scientifically, the Moon preserves records of early solar system history that Earth's active geology has erased. The far side offers unique astronomical observing sites. Samples from diverse locations will constrain lunar and terrestrial evolution. Studying how to live and work on another world provides knowledge essential for eventual Mars exploration or other deep space activities. Economically, resources on the Moon might support space activities, reducing costs by eliminating the need to launch everything from Earth's deep gravity well. A lunar refueling depot could enable missions to asteroids, Mars, or beyond at reduced cost. Manufacturing in lunar gravity might enable products difficult to produce on Earth. Whether such economics work out remains to be seen, but the potential exists. Geopolitically, lunar capabilities demonstrate technological sophistication and leadership. Nations establishing lunar presence gain prestige and influence. Competition for lunar resources or strategic locations could create tensions, but it could also spur technological advancement and international cooperation if managed wisely. The Moon could become an arena for demonstrating peaceful cooperation in space, building trust that might extend to terrestrial relations. Inspirationally, the Moon represents humanity's first step toward becoming a multi-world species. Living permanently beyond Earth, even on the Moon only 400,000 kilometers away, requires developing technologies and social structures enabling people to thrive in space. These capabilities, once developed, potentially apply to Mars, asteroids, or even interstellar generation ships far in the future. The Moon serves as our first practical classroom for learning to live beyond Earth. The vision emerging from multiple space agencies and companies, involves lunar bases housing dozens of people continuously, with regular crew rotations, resource extraction operations providing water and propellants, science investigations addressing fundamental questions, and transportation infrastructure supporting activities throughout cislunar space. Whether this vision materializes depends on sustained political will, technical success, cost reductions, and international cooperation. But the combination of governmental programs and commercial interest creates conditions more favorable than any time since Apollo. Some proposals envision lunar settlements growing to hundreds or even thousands of people over decades. Such settlements would require extensive infrastructure-sealed habitats, providing Earth-like environment, power systems supplying megawatts of energy, food production facilities growing crops, manufacturing systems producing tools and spare parts, hospitals providing medical care, communications networks connecting bases and Earth. The logistical challenges of supporting large populations on the Moon are enormous, but proponents argue that with sufficient investment and technical development, they're solvable. Others caution against over-optimism, noting that space colonization dreams have been articulated for decades without realization. The costs may remain prohibitive, the challenges insurmountable, or the benefits insufficient to justify investment. Political priorities shift, budgets fluctuate, and technical problems sometimes prove intractable. However, the current convergence of governmental programs, commercial interest, and technological capability appears stronger than previous periods, giving this era of lunar exploration a reasonable chance of achieving sustained presence, even if grander settlement visions take longer.